Okay. So good afternoon once again. I think we can start now. Can you hear me, please?
Yes, sir.
Yes, please, you can.
Okay, perfect.
Yes.
Okay, so I'm not going to do revision from the very first that we started the class. Excuse me. I'll just do a very short revision from where we ended the last time. And so I'll just go straight to that, and then I'll do a very fast and a quick revision from there. Then we start today's class. Okay, so last week we did something we call the current electricity, and what we were trying to bring on board for our understanding, something we call the current, something we call the energy, and of course something we call the resistance, and they are all related one way or the other. Is that okay? We have something we call energy that is pushing the electrons, and in the process of pushing the electrons, it causes it lets it move with respect to time, which causes current. Is that okay? And even when current too is moving, there's also a particular force that is actually trying to restrain its movement. Is that okay? And that is called the resistance. And it's like you being in a children's class and they are all trying to say exit from the class with one door in, and you are at the entrance trying to prevent them from going. And that is what the resistance is doing. So we started talking about how these charges move with respect to the current, and we started discussing what the current formula is. And we spoke about something called the current density, which I was telling you that as the usual density where we have a particular mass with respect to volume. This time around, we are talking about current with respect to the cross-sectional area in which it moves. Is that okay? That is why we have I over A. Another thing that we can also talk about, no, another thing that we spoke about, let's use the English word well, is the drift velocity, where I told you that we don't have an electron moving straight to the position that we want it to. Whatever being the case, during its movement, there's a form of a collision somewhere, and that one changes the direction or the path of the particular charge. And in fact, all the small paths that it has taken to reach its destiny, we can find the velocity of it, something like the average velocity. Is that okay? And that is what we call the drift velocity. And I gave a very typical example, like you sending your child and the child is not going straight to the shop or where you are sending the child to, but the child stops at different vantage points of his or her choice to do anything that he wants or she wants. Is that okay? And at the end of the day, it's going to prolong the movement in which it's going to reach there. But we want to know the small velocities that it used at its point of stop. And that is what we are looking at here. So it moved here, it used a particular velocity to move here, it used a particular velocity to move up here, it used a particular velocity to move down here. All these velocities up to this end is the average velocity we are looking for. And here is what we call the drift velocity. And it's very important because in electrons in a particular material, that is how it also behaves. You will not get energy being given to this one to go straight to this end. As it's moving, it will meet its neighbor electron. There's going to be a collision. It moves again, it's going to be a collision. Is that okay? And at the end, it will cause this movement or zigzag movement around it. But what we have to put in mind is the electron knows where it is going. So even with all the collisions that is happening, it still has its destiny. Exactly. In fact, collision can even happen, then it will come back again, then it will go, So we have to take note of that. And we solved some questions. I think we did this too. And we spoke about something we call the circuit. And this is a very close loop. I brought something called the ammeter in, the voltmeter in. This is used to measure current. This is used to measure voltage. And I showed you how the ammeter and voltmeter is connected when we are dealing with such a circuit. And I told you that whatever being the case, the ammeter is supposed to be in series connection. Whatever being the case, the voltmeter is supposed to be in what? Parallel connection. Exactly. And this is a very physical and a demonstrative manner of it. I think next week we'll meet. The following week you are doing practicals, so that one will be communicated to you. But those who that will be meeting, we will, and I think all of us will do the same thing. We will be doing these connections, and you will see how it works. Is that okay? And this is a typical multimeter. And if you've not seen it before, during the practical session, we will show it to you. And I think we did this question, and ohms came in, where a material like ohmic material was mentioned. And I told you that anytime we have from Ohm's law, anytime we have a voltage and a current being measured, we expect it to be in a linear graph like this. But if it's not an ohmic material, it is not going to behave like that. It's going to behave something like what we've drawn here, like an exponential form. Is that okay? And this one, we will do it very, 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 very soon. I think your second year, we should be doing electronics. You'll be seeing this one. And a very typical example of a material that can behave like this is a semiconductor. Is that okay? And a very typical example of a semiconductor that behaves this way, it is the diode. Is that okay? So they all behave this way. Please, can I go on? You can give me a thumbs up if you are okay so that I go on. Great. Then we spoke about resistivity. So there's collisions of the electrons or the charges in the causes the resistivity. Is that okay? Because it slows the movement. And the process of slowing the movement, that is what resistivity comes out. And we spoke about this formula where we can relate resistivity, that is the rho, the length of the material, the cross-sectional area of the material, and of course, the resistance of the material. Is that okay? Which is very important. And you have to know that we can bring another parameter like a conductivity in, because resistivity is inversely proportional to conductivity. So when we don't see the rho here, it means it's 1 over conductivity. Is that okay? Which is the same. And in fact, every material has a specific resistivity value. Is that okay? Copper has a specific resistivity value. Aluminium, all of them, they have a particular value for it. So when you are doing this kind of a calculation, unless you are asked to find the resistivity itself, if you are doing this kind of calculation, like finding the resistance and you are using this formula, it means you're going to need these parameters to help you go through. And I think we solved this question. Then I told you that we have a relation between temperature too and resistivity. As far as there's a correlation going on, temperature has an effect on resistance. And there's a formula here. I've not added any question under this, but I'll try and update the slides maybe so that you see how a question like this will be formed. And apart from the resistivity relation with temperature, we can also relate resistance and temperature, because already resistivity and resistance are related. Is that okay? So we can do that relation too here. Then another interesting thing surfaced. That was the power and electrical energy. And I told you that in your room or in your house, you have a whole lot of gadgets that needs a form of energy. Is that okay? And that form of energy is very, very, very important because without that energy, that gadget is not or device is not going to work. Because what the device is doing is converting one form of that energy to another form for you, like the refrigerator is transferring one form of energy to the coldness that you want. Is that okay? If you are using a microwave to heatness that you want, if you are using a pressing iron, you want to heat it. Is that okay? So convert that electrical energy to that form of a heat for you. Is that okay? And it's very important. But the consumption is very related. And a typical example like Ghana here, our consumption rate is kilowatt hour. Is that okay? Because as usual, our power is in watt. Then we add a prefix called a kilo. Is that okay? And with rate to how you are using it, we add the hour. Is that okay? So this one becomes the what? The electrical energy unit in terms of what we need here. And another important thing that we have to also know is that this kilowatt hour can be represented in joules. Is that okay? And with this simple convention, we can just convert it in joules. And I think we solved this question. I don't know whether we did this. It's either we did it or I asked you to go and do it. And we looked at EMF. So EMF came in when we were discussing the fact that if I buy a battery of 9 volts and I use a multimeter to check the 9 volts, I'm not going to get 9 volts. I may be getting about 8.5 volts. So the thing and the question is, the very big question is, where is the other 0.5 volts? Where has it gone to? Is that okay? And that was what we were discussing, and I think we ended. And they all a very common way. Is that okay? Like the usual way. If I buy a 9 volt, I'm expecting 9 volts. But now I buy a 9 volt, I'm not getting the 9 volts. And we concluded that every battery has a form of internal resistance in there. Is that okay? And that one too reduces the EMF of that particular battery. So in terms of doing a full circuit calculation like this, we have to bring in the internal resistance and of course our normal load resistance that we are also talking about. Is that okay? You see, for the previous examples, anytime you are doing a calculation like this, you don't consider the R. But now we understand that there's a small R in there that is affecting the resistance or reducing the voltage of the battery one way or the other. Is that okay? So henceforth, anytime you are doing a calculation, you are going to consider this internal resistance, unless the question didn't or is not bothered about it. Apart from that, we are going to consider it. And we had a formula for it as this, and we re-derived it to get our I to be equal to what? Our EMF divided by R. This R is the external resistance itself and the internal resistance in the battery. And I think I gave this question out. Please, did we solve this? Or we don't remember? We didn't solve it. Oh, okay.
No,
They will
please.
say we solved. Ellen is saying we solved. Okay, I'll say we didn't solve. Okay. So go through this one yourself. Go through this question yourself. Then I think we did resistors in series, and we did resistors in parallel. And I asked that we should solve these questions. Please, the questions, let's be solving them, I beg. And I think we ended here. But before we start, I want to ask the class a question. If we are given a question like this, or better still, let me go back a little. If we are given a question like this, can we solve? Find the equivalent resistance between points A and B in this figure. Is it possible to find the equivalent resistance?
Yes,
As in the total resistance. Okay.
it's possible.
Very good. So I'm giving the class only 5 minutes. Let's try our hands on this. And for a very sharp recap, anytime you are given a parallel resistors to find the total resistance, this is the formula. Is okay. 1 over R equals 1 over R1, R2, R3, R4, depending on the number of resistors given. Sorry. And if you are doing it for that of a series combination, it's just R1 plus R2 plus R3 plus R4 and henceforth. Is that okay? Depending on, of course, the number of resistors given. So if we know this, let's try our hands on this. Only 5 minutes. Please, let's all try our hands on it. Just try doing something. It helps. Is that okay? So everyone should try doing something for me, I beg. The important thing that we have to note here is, you see, there are a lot of connection going on here. Some of the resistors are in series, some of the resistors are in parallel. And I advise that that is the first thing that we have to check. Is that okay? So when you take something like the 7 ohms and the 10 ohms, are they in series or they are in parallel? And when you take the 4, okay, when you take the 4 and the 9, are they in series or they are in parallel? And in fact, we want to know the resistance of all of them. Is that okay? So let's be very careful how we solve this.
Let's find out. This will be yes, we are. Equals to
Okay, I have 2 hands up. Okay, so Frank Paddy. Hello, Frank
Hello,
Paddy.
sir.
Yes, sir. Can you
Yeah,
help me how you went through?
yes, please.
Mm-hmm.
Okay, so for the effective resistance, I first of all calculated for those in parallel.
Mm-hmm.
Yes, and I had 17.1 ohms. And then
But sir, hold on.
okay.
Right now I have 4 resistors here. How
Yes.
many of them are in series and how many of them are in parallel?
Two of them are in parallel.
2
two
of
of
them.
them are in
Okay. Which
Yeah,
and
that
which
is
one?
7 ohms and 10 ohm resistors.
Perfect. So 7 and
Yes,
10, they are in parallel, right?
parallel.
So it means we have to combine the two of them to become one.
Yes,
Then when we
then they
finish,
will,
it becomes series with all of them. Is that okay?
yes,
Yes.
Perfect. So please, class, if you are not understanding, I'm explaining it as Sepade is giving his answers. So we have to combine this one, the 7 and the 10, to become one resistor. Is that okay?
Yeah.
So
Yes.
after calculating the answer you will get, that is what you are going to get for the 7 and 10 combining.
Yeah.
Then when we
Yeah.
finish,
Then
we've
becomes
combined it together. It
out.
becomes series with 4 and 9 ohms. Is that
Yes.
okay? Mhm. So now, Sepade, let's continue. How did you calculate for the parallel connection?
yeah. So for the parallel, we know the formula to be 1 over the total resistance equals 1 over the first resistance plus 1 over the second resistance. So after computing everything, I had 17.1 ohms.
Okay.
Yeah.
17.1
Then
ohms. That is
yes,
too short. When you find the parallel connection, this one and this one, what are you getting?
the power connection for the two, I had 4.1 ohms.
4.1 ohms. So
Yes,
now the 1 over R equals 1 over R1, 1 over R2. It becomes 1 over 7 plus 1 over what? 10,
yes.
right? So hold on.
So at the end of the day, we get 70 over 17.
So say, hold on, so that
Okay,
those who are not understanding will follow up. Is that okay?
all right.
So this is the formula for the power connection. R1 plus R2, but I'll just write the 7 straight away there, plus 1 over 10.
Yeah.
Am I doing the right thing, Sepadi? Then when we
Yes.
finish, 1 over 7 plus 1 over 10, what are we going to get?
70 on 70.
No, 70 on 17, rather.
70 on
On
17.
17, yes.
1 over 3,
17
No,
on
1 over
70.
R,
oh, okay, you
Yes,
get
70.
17 on 70.
70.
17 over
Well,
17.
Yes,
Now, when we finish, this is not the answer for R, because what we have at the other side is 1 over R. Is that okay?
so
For
Yeah.
us to find
reciprocate.
the actual, very good. For us to find the actual R, we have to find the reciprocate of it,
R
or
is
the inverse.
70 on 17.
Very good. Now the R becomes 70 over 17. And in decimal places, what are you going to get?
4.1176. 1,
4.1176.
1. That is 4
So
76.
let me just do it 1.8. Is that okay?
Yeah.
And I get this one ohms. Now the answer I've gotten is for only this resistors. Is that okay? So now we've gotten a particular value for this resistor here. Is that okay? Now we are not done, because the question is asking us to find the equivalent or the total resistance between A here and B here. Is that okay? So it means after getting the middle one, now it becomes in series with the what? With the 4 and with the what? And with the 9. And for series connection, we have our R here. Oh, my R is too big. To be equal to what? R1 plus R2 plus R3. Now here my R1 becomes what?
4.118.
Okay, so let's take this one as the 4. Is that okay?
Okay.
Then the R2 becomes the middle one. That is the 4.118.
Yes.
And the R3 becomes the very last one. That is what?
9.
That is 9. Perfect. And from here, can someone help me with arithmetics?
Yes, we have 4 plus 4.118 plus 9. This gives us
17.11.
17.118.
17.118.
Ohms.
Yes,
Yeah.
ohms.
17.11. Perfect. So you see, this one is very straightforward. So we have to look
Yes.
at a diagram that will be given very, very well. And that is what is going to inform you to do your calculation. Is that okay? Where you have series, you can combine. Where you have power, you can combine and you need to do. Now let's move on to the second one that we have to do. We are asked to find the
The
what?
current in each. Find
The
the
current.
current in each.
Hmm. This is a very nice question.
Each
So we want to find the
resistor.
current in each resistor if the potential difference, that's the PD, is 34 volts
34.
applied. How are we going to go through this one? The first current passing through this voltage, what are we getting?
You get 8.5
8.5, okay.
ampere.
Hmm. How did we get the 8.5?
So I think we have the formula V is equal to IR.
Mm-hmm.
So we are looking for I.
Okay.
So we have V over R.
Mm-hmm.
And then the V was given as 34 volts. So we divide by the R, which is the 4.
Okay.
And you get 8.5.
8.5, okay.
So we do same with all the other resistance.
Resistance, okay. Thank you. Any different answer? So any yes or no, or we are all in the middle, either yes or either no. Okay. So this is a good attempt, but it is wrong. The reason being that when we are talking about current, let me show you something. Current that is passing through a resistor that is connected in series. You see, the same current that is passing through this resistor is the same as the one that is passing through this resistor. Is that okay? It doesn't
Okay.
change. So if we are doing this kind of a calculation to find the current, you don't have to use the individual resistors. Is that okay? You have to use the total resistance.
Resistor.
Is that okay? Supposingly,
Okay.
the calculation we have to do, they are in parallel connection. How Sir Charles, was it Charles or someone?
Charles.
Yes, how Sir Charles solved it could have been the very best position or illustration. Is that okay? We take the individual resistance to calculate for the current. But looking at 4 and 9, they are in series. So it means the same current that will pass through this one will be the same as the one that will pass through this.
Okay.
And the easiest way
Okay.
to go through this one is using the total resistance.
Okay.
Okay, so I think that's what I did initially.
Okay. And what did you get?
1.898 amperes.
1.98 amperes. Okay.
Sir,
Mm-hmm.
I want to ask a question.
Please ask your question.
Okay, so it means that the total resistance that we had in A,
Mm-hmm.
that is what we are going to use to calculate.
Mm-hmm.
So we are going to divide the 34 by the 17.116.
34.
Yeah, 34.0 by 17.11.
Mm-hmm.
Yeah, that's what
to
you're
get the,
going to use.
to arrive at the final answer.
Yes. So that will be when you divide, you are getting about 1.9. Someone gave an answer. 1.9 what?
1.8.
1.9.
98. And in fact, when you get the 1.98, that is the total resistance across the circuit. Is that okay? And because
Okay.
because 4 and 9 are in series, the 1.98 passing through here will be the same as the 1.9 passing through this one end. But the middle here is going to be different because it's in parallel connection.
Okay.
Is that okay? So the first thing that we
Okay.
have to know is that anytime we are doing a series, we have a series connection. We have the same current passing through the circuit for all the resistors. But when we have a parallel connection like what we have here, kindly check what I'm showing you here. You see, the current enters a junction A. It divides. We have I1 and I2.
Okay.
Is that okay?
Okay.
So current is different when it comes to power connection as compared to series connection. Yeah, say David, your hands is up.
Well, so I've asked the question that you explained to me the figure that we're going to use to do the calculation.
Please come again with what you just said.
I asked about the figure that we're going to use to do the calculation. Then you've explained
Okay.
it.
Okay, I've explained it. Very good. So we will not finish answering this. I'll still leave this one again for us to try it. Is that okay? The next time you meet, I'll ask about it. So calculating for the resistance, I think we are all good. The only thing left is finding the individual current passing through the circuit. And I'm telling you that we have to use these principles to guide us do that. Is that okay? You have to know that current entering a junction device, either device the same or device with a particular proportion. It depends on the resistance of the resistor. Is that okay? But when it comes to voltages, it's the same for the two. The same way as what is happening with the series connection. Is that okay? So let's just go through the conditions here, and we use it to solve the very last one. But I've highlighted how it's going to be done, so just play around it. Is that okay? I'll ask the next time you meet. Are we all okay? I want to move on.
Yes, please.
Very good. Now let's look at something here. Another trial example. If we are given a question like this, how are we going to go through? Any idea?
Sir, please, what are we finding?
Here we are finding for current.
Current.
I1, I2, I3.
So,
Okay.
please, we didn't hear you.
We are finding for current. Any idea how you solve this question? We want to find for current. It's two different schematic diagrams, A and B. And I want to find the current I1, I2, and I3 for the question A. And question B too, the same. Any idea how
Okay.
you go through this?
So, are you going to use?
Hello, I'm not hearing anyone. Hello? Yeah, Sazuma, I'm listening.
Okay, yes, sir. For the what I'm saying is that for the first loop,
Mm.
the one containing 14.0 voltage, we are using two batteries here. So 2 voltage. Okay, let me put it that way. So what I'm suggesting is that we have to find for each individual loop.
Okay. So say
example,
we
B,
take the
C,
first
D,
one
and
here,
F,
then we
or
take
A,
this one.
B, B, C, and A. And from there, we can also take E, F, C, and B. Okay, after we also find that one. So we can then consider whole loop. For example, E, F, D, and A.
Okay.
In fact, unless I put it on a paper, the thing is getting so. No, there's a tedious work there. It's like if I keep on learning, I'll confuse them more.
Oh, so Azuma, we can give you all the hours so that you help us. So Azuma, we can give you all the hours so that you help us.
Then I have to put everything on the paper before.
Okay. But any different ways or ideas how you think we can go around this question?
Is given which is in parallel.
Okay. Okay, so maybe let me help you. So when you are given a question like this, we have a favorite man who helped us a lot, and that is Ketchup. Is that okay? So we have to use the Ketchup rule to solve a situation like this because this is a very complex DC circuit. Is that okay? Like Azuma said, when you look at even the top one, we have two different potential difference. We have 14 volts, we have 10 volts. We still have two different ohms, 4 ohms and 6 volts. Calculating for the current here, it's a whole lot of things here. Is that okay? When you look at even the down one, two here, it's a whole lot. And now the current that is flowing through the first one is the same as flowing through the second one. And it makes it so complex. So the only situation at hand that can help us solve this kind of a procedure is what we call the catch-up. So we will follow some rules to understand. When you finish understanding, I'll come back to this question, then I'll leave it for the class to try. Is that okay? Can I go on?
Yes, please.
Please.
And the first rule that we are going to learn is what we call the junction rule. Is that okay? And what this rule is telling us is that anytime we have a current entering a junction, as a noun, I've explained what a junction is, so you know. It must be equal to the sum of the two current exiting the junction. Is that okay? So this one, the I1 entering, should be equal to the sum of I2 and I3. Is that okay? Supposedly, after reaching the junction, supposedly we had 4 exiting. So it will be going to be all the summation of all the 4 exiting equals the I1. Here is only 2 exiting, so 2 of them equals the I1. Is that okay? That is the first rule we have to know. That is the Kirchhoff junction rule. Can I go on? Okay. The next one is the potential difference rule. Is that okay? Now I'll go through this one, but let me go through the slides, then I'll come back again. Now, if we are going to consider a loop, it's either we consider it a clockwise way or an anti-clockwise way. Anytime you are given a question, you have to consider a loop. Is that okay? So you will decide whether you're going to choose a clockwise or anti-clockwise. And when we say clockwise direction is how the analog clock moves. You see the clocks on the wall, how they move. That is that direction. That is a clockwise direction. And anti-clockwise is the opposite of that direction. Is that okay? So we have to look at 2 ways. And as of now, I've explained that first junction rule to you. So I'm going to the second subsequent ones. Now, the first thing that we have to know is after choosing your loop, supposing what we have to consider here, we are choosing the clockwise direction. If your loop is the same direction as the current, it means your voltage or your potential difference is going to be negative. That is the second rule. I'm repeating. If the loop you have chosen, supposing we have to use anti and clockwise, is that okay? We have taken clockwise throughout. If I take clockwise, and in my circuit diagram, the clockwise is the same direction as what I have as the current, the potential difference becomes negative. And you know, always we have V cos IR. So here it becomes negated. Can I get a thumbs up so that I move on?
Please, what is the loop?
Okay. So someone is asking about the loop. So let me go back. So you see this question. We can decide to choose a loop for ourselves. Is that okay? Already, this whole thing here is a loop. Like it's a full circuit, like a loop closed up. Is that okay? But the loop movement, we will just decide whether we are going to use a clockwise way or we are going to use an anti-clockwise way. Is that okay? And if we choose a loop for the calculation, the first one is going to be the same as the second one. And you know, when you're having a question like this, we can see that clearly we have two loops here. We have a closed circuit here as one. We have another closed circuit here as two. And you can even imagine and remove the one at the middle here. We will get another closed circuit here as three.
Okay.
Have I managed to confuse you enough, or it's fine?
Yeah, I got it. Okay.
Very good. So that is the loop that we are talking about.
So the loop is like something like a circuit diagram, or
This is a circuit diagram.
Enclosed
Circuit, perfect.
Okay.
Is that okay? But
okay.
here, so that is what I've shown you. We can choose one, the top here as one loop.
Yeah.
That is E, F, C, B.
Okay.
That is going to be one loop. We can choose another loop down here as B, C, D, A as another loop.
Yeah.
And in fact, we can even ignore the one at the middle here and choose a E, F, D, A as another loop.
Okay.
Is that okay?
Yeah.
So, and I'm saying that the loop movement, you will choose a random one depending on the individuals. And in fact, you are going to get the same answer. You can choose a clockwise or you can choose an anti-clockwise. Is that okay?
Yeah.
And I'm telling you that anytime you choose, say, a clockwise, this is a clockwise way, right? And in the loop you are dealing with, the direction of the current is the same as the loop that you've chosen. The potential difference for that particular end becomes negative. That is the first thing you have to put in mind. Let's move on. But supposing the current passing through the resistor, the direction is opposite your loop. You see, this direction is going anti-clockwise. My loop I've chosen is going clockwise. Then the potential difference here becomes what? A positive.
Positive.
It's reverse the direction of the current.
Yeah.
Now, that is the movement of the current with respect to the loop. Now, if you have your potential difference, that is the EMF itself, as from negative to positive with response to the loop, a situation like this, it becomes a what? A positive. So anytime my loop is going clockwise, and the clockwise here is from negative to positive, my EM field becomes positive. These things are not something the laws are not something you, or the rules are not something to be given to you in exam. So this one you have to know it in your head so that you don't have to refer to any chart. There's no chart you refer to. Is that okay? You have to know that these are the catch-off rules and these are how it's used. So please keep it in mind. So I'm repeating. If you have a situation where your EM field is from positive to negative, response to the loop, it is going to be positive, the potential difference. But situation where this time around is from positive to negative. You see, this one was from negative to positive. Now with our loop here, is from positive to negative. Then it means our what? Potential difference becomes what? Negative here. Can I get a thumbs up, or we are all confused? Okay. I'm going back again. So the catch-off law. You see, everything that I went through, these are the summary of it. Is that okay? And this is when we are tracing a clockwise loop. The first one is telling us, it's a junction rule, it's telling us that the number of current that has entered the junction is the same as the summation of all the current that has exited. So here our formula is I1 equals I2 plus I3. It's one thing there. Now let's look at the ones we have here. If it is a clockwise, these are what we are going to get. The first rule is telling us that.
Please, can you zoom it a little bit?
Okay.
All right.
Is that okay? If it is a clockwise loop, and the clockwise loop is with the direction of the current passing through a resistor, we are saying is the potential difference is going to be negative. Now, if it's opposite the direction of the current, is going to be what? Positive. If it's the same direction, it's going to be negative. Opposite the current is going to be what? Positive. The same clockwise direction. If it's clockwise direction and our EM field is from negative here to positive here, it means our potential difference is going to be what? Positive. If it's a clockwise and we are moving from positive to negative, our potential difference is going to be negative. Now let me ask the class a question to know if you understand. Supposing we are not using a clockwise loop and we are using anti-clockwise, what is going to happen to this potential difference?
Positive.
Positive, perfect. So the potential difference is going to be what? This IR. What is going to be, what will happen to this potential difference?
Negative.
Equals minus
Negative. Is that okay? V equals minus IR. Thank you. What is going to happen to this C?
Negative.
equals minus EMF.
Is that okay? Perfect. Then the last one here is going to be what? Positive. So if we have drafted this thing down, now let's go to the actual question. If that is the case, only the A, the circuit A. Let's find for I1, I2, and I3. And maybe because we want to use uniformity's sake, maybe let's all use clockwise direction. And we are using these only two loops. The first loop here and the second loop here. Clockwise direction, clockwise direction. Can we do it? Or you will need help?
We'll try.
Okay, try for me. So let's try. So just write the formulas down. First, use the junction rule. When you finish, you use the potential difference rule. Is that okay? The junction rule, look at the current here, the one that is entering a junction and the one that is exiting a junction, and derive a formula for it. When you finish, look at the current and the potential difference, and you also derive another formula for it. Please, are we doing it? Oh, okay.
Yes, sir.
So very good. How I really wished I'm around, and I'll be checking what everyone is writing. Let's try our hands on it, Abeg. Yeah, Sir Jesus.
Yes, sir.
Yes, sir.
Good afternoon.
Good afternoon, sir.
Please, I'm a bit confused
Mm-hmm.
about the first, the first diagram where we
Mm-hmm.
take a look of E, phi, or F, E, the current over there. Please,
Hello, sir.
Yes.
I could see that the I2 and the I3 are moving in the same direction. When I
Mm-hmm.
consider I1 hitting the junction, I was thinking it will move in opposite direction. I2 and I3 on the loop of E, F, D, E.
Mm-hmm. Can someone help Sir Jesus here for me?
Please, sir.
Yes, sir, Francis.
Sir, you know what?
No, tell me.
Please, let's all solve one, then the
Mm.
best the another one.
But let's first go through Jesus' question.
Okay.
Uh, so he is confused about how. Right now, I've explained about 4 rules to you.
Okay, for the current one,
Mm-hmm.
I saw it as I1 is equals to I2 plus I3
Okay.
because
Are
I
we all
saw
getting
that.
the same?
This is what you say.
Are we all getting the same? No, I'm asking the class if everyone is getting as you
Okay.
are.
Yeah, for the
So,
first one, that's what as well.
That I got it right. Oh.
okay, so Sir Kwabena is saying the current or the junction rule formula, from the junction rule formula, we are going to get I1 equals what?
I2 plus I.
I2 plus I3.
Can you justify what you are saying?
No, 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 no.
I
It's
saw
good.
that. Please, are you there?
Please, I'm here.
Uh-huh.
Minus I2.
I1 is the same current that left junction C, right? So it moved from C downwards to 14 voltage. Then it descended to be the I2.
Any different suggestion? Sir Kwabena, I understand what you are saying, but I want a different suggestion.
Okay.
Mm-hmm. Or we are all not understanding.
Hello, sir.
Yes, sir, please, I'm listening.
Please, if Kwabena is saying that I3 is the one that moves through D, A, as B, there is a junction over there. So it cannot be the same as the I2 that will pass through the 14. That's C, returning from F, that is the same as C2. I don't really agree with him on that. That is why I'm looking at the direction of the current, the I2 and the I3.
Okay. So from your perspective, what is going to be the equation?
Hello, sir.
Yes, sir, please, I'm listening.
I think the equation should be I1 equals negative I2 plus I3.
Okay.
Because at junction C, I2 is expected to move up, but it's rather moving the opposite direction.
Okay.
So that would be negative in my perspective.
I think, let me write the actual answer for the class. So from our first law, this is going to be the first equation that we are going to derive. And it's very correct as what, is it someone who answered it? The one who just spoke right now.
Francis, please.
Okay, Francis. So it's the same as what you just said. This is the junction. And we are saying that the amount of current exiting the junction is the summation of the amount of current entering the junction. Or the amount of current entering is the same as the amount of current, the sum of it is the sum amount of current that is exiting. The first thing you have to do is to identify a junction in a situation like this. Is that okay? When you look at this whole circuit diagram, we are dealing with only A. Is F a junction?
No.
No.
F is not a junction. Perfect. E2 is not a junction.
Yeah.
So how many junctions do we have in here?
2, B and C.
Perfect. B and C. Now let's consider, say, the B. The B will be the C will be very easy. Let's consider junction C. How many currents are entering junction C?
Two currents.
2. I1 and what? I2.
I2.
And only one current is exiting. Is that okay? So from the rule told us that the one entering is the summation of what? All the one exiting. Or the one exiting is the summation of all the ones entering. Either way is fine. Is that okay? But at the end of the day, we expect the one entering supposed to be at one side of the equal sign and the one exiting at one side of the equal sign. Is that okay? So the one exiting is at one side of the equal sign. The one entering is at one side of the equal. Voila. And we are done with what? Getting the first equation. Who is confused here?
Please, can you go over again?
Okay. Can someone help me go over again?
Yes, sir.
Yes, sir.
Help me.
So who is talking? Okay,
Please
so
go ahead.
according to what Say is saying, and if I understand it clearly, Say is
No,
saying
right
that
now, Stephen, hold on. Use your understanding to explain. Don't let it seem like I'm deceiving you. According to how I understood it.
okay, so according to how I understood it, from the rule that was given, it says that if the current is moving away from or it is leaving the junction, is the summation of the current entering, or if the current is entering, summation of current entering the junction is the is equal to the current leaving. So if that's the case, the equation should the other somewhat says something. It should be negative because of the arrangement. We realize that the junction here, it is current 1 and current 2, which is entering the junction, and only current 3, which is leaving the junction. So meaning that current 3 is equal to current 1 plus current 2, meaning from the rule or from the rule given. So it's just a principle. That is how I understood it. Thank you, sir.
Okay. The person who asked the question, is the person understanding still, or
So can we also say that I2 plus I1 equals to I3?
yes,
Since
of course.
I3 is
Yes,
leaving, can
I
we
think
say
that
so?
is what we say. Yes,
Okay.
please.
Okay.
What we need right now is the one entering should be at one end of the equal sign, and the one exiting should be at one end of the equal sign. Is that okay? So whether I1, I2 goes at the left and I3 goes right, they are all the same, right?
Okay.
Yeah.
Sir,
Yes.
initially we were confused because we saw I1 that it is leaving. You see, when
Is
it
it
reaches, I said we were confused initially that when it just step out of C, that junction, if you just go down or up, you understand? That is how we saw it, not knowing that it will reach at C, then the I2 to also enter. It's only I3 which is leaving, so hence the equation is okay.
Okay. Now let me ask the class a very quick question. We are not doing the B, but let's consider the B. How is the junction rule formula going to be for the B, for this circuit?
I2 equals I1 plus I3.
True.
Yeah.
Yes. Yeah. I1 and I2 are all leaving. And then I1,
I2.
I1 and
and I3
I3,
are leaving.
they are leaving. And then
I2 is
I2 is
entering.
entering. Okay.
Are we okay now?
Yes, sir.
So,
Yes, sir.
Yes, sir.
So yes.
so I2 equals to I1 plus I3. Okay.
Sir Jesus is always giving comments. I'm not hearing him talk. He just giving me thumbs up, either thumbs up, thumbs down, or celebration. Okay. Anyways, let's go.
I'm not talking because I just don't want to distract the class. Whatever
That,
somebody said, still is okay then.
but even if
I
it's wrong, you still give thumbs up as correct. When someone gives another correct one, then you give another thumbs up.
no, the person is trying, so I can't say the person is wrong, you know.
Okay, that's fine.
So please, wait, doing this question, I'm trying to do it, but I want to understand certain things. Are you
Ask.
going to solve the resistors in parallel? Because
Okay.
taking the first loop,
Mm.
you can see that the resistors are in parallel.
Now, hold on to this question here, and let's follow Kirchhoff procedure. We have some of them in series, some of them in parallel, but we are not going to bring that parallel and series situation here because this is a full complex DC circuit. Is that okay? So
Sure.
we will go through this one particularly and purposely through Kirchhoff. Is that okay? And I told you
Okay.
that here we have two loops. We have the one at the top here and one at the down here. And we are going to consider the direction that we want to move. Is that okay? Whether clockwise or anti-clockwise. In fact, maybe let's use clockwise. So this is my clockwise direction. Is that okay? It goes this way. I'll use the same clockwise down here. I advise that loop you use it throughout. So clockwise is up here, clockwise is down here. Now let's first talk about the first loop. When I finish, then we'll go to the second loop. So we are going to derive an equation for the first loop, derive an equation for the second loop, and at the end of the day, get 3 equations. Already, we've gotten a first equation. So another equation is going to be derived, another equation is going to be derived. Now, let's go through. I'm going to start with the potential difference at the top here. Is that okay? Now, from my loop movement and the potential difference here, is the potential difference going to be positive or negative?
It's going to be negative.
Negative.
Hold on, let's go back. Let's all write this thing down. If it's going clockwise direction, anytime we are from positive to negative, we get negative. From negative to positive, we get positive. The direction of the loop is as this, we get negative. Opposite direction as this, we get positive. Have we all written this thing down? Let's just do a very small draft right now, please.
This. Usually from positive negative to clockwise.
Can I move?
Yes, sir.
Perfect. Now to our question. If I have a positive here, sorry, let me use a pen here. I have a positive here and my loop is going clockwise. It means if my loop is going clockwise, I'm going to move from positive here to the negative here of the potential difference.
Negative.
So what is going to happen to the potential difference, positive or negative?
Negative.
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 Do you all agree to that?
Yeah.
So now I'll write my negative 14. Now, right after this potential difference, I'll go straight and come and meet this resistor there. Now, the resistor here has a resistance of 6 ohms, and it has a particular current passing through that resistance, that is I1, because all this end here is I1 that is passing through. Now, let's relate the I1 passing through this resistance and my loop. What is going to happen? Am I going to get a positive or a negative?
Positive. Because the direction is opposite.
The direction is opposite. So you're going to get what?
A positive, yes.
Are you sure? Are we all saying it's positive?
No, we didn't get it.
It's positive.
So I'll get positive here.
14 plus.
And
Okay,
because
I2.
we are talking about
I2.
potential difference here, if I want to find potential difference, it's V equals IR. I can find the potential difference here.
So the
My
I2,
R
where
is
is that
this,
for?
my I is this. So I'm going to get 6 I1.
Then why did you get the I1?
Can
So
I
this
move
one
on?
plus.
Or we are still thinking about it?
I can move on.
When you look at, let's look at this one. Look at the direction of this loop. And let's look at this one comparatively.
Okay.
Is this moving the same direction or opposite direction?
Opposite direction.
Opposite direction. Is this one moving the same direction or opposite direction?
Same direction.
Same direction.
Same direction. Now let's move to the question here. Is the direction of this one and this one the same or opposite?
The same.
Opposite.
It's opposite.
Yeah, sure.
Opposite.
It's opposite.
Okay, yeah. Okay. Yeah. Yes. This one is okay. We are moving from the top. Okay.
I think it's moving the same, or
Same direction.
please let's look at this one very well.
The
So
same direction.
the current is moving this way. My loop is also moving this way.
The same.
The same.
Is it the same or opposite?
The same.
The same.
It's opposite.
Opposite.
This is
Next
opposite.
question. Let's go on. Okay, what if I bring a current direction like this? The same as this loop. Is it moving the same or the opposite?
It's the same.
The same.
Mister, it's the same direction.
So, sir, please, I think the loop is moving opposite the direction of current 1, but in the same direction of current 2.
Now we are not considering current 2, we are considering current 1 because it's current 1 that is passing through. It's current 1 that is passing through this resistance.
Yes, please.
Is that okay?
Sir, please, it's opposite.
Please, sir.
No.
Please, sir.
Yes, sir.
And the loop we are dealing with now, you know, the current is flowing from positive going. But we have considered it to be moving anti-clockwise. So that is why we are saying that it is opposite with the current.
No, if let's look at the what I've drawn at the top here. If we are able to justify what is at the top here, I think we should be fine. Or maybe let me go back here. If I have a direction like this, and I have another direction like this, I'll call this direction as direction 1. I'll call this direction as direction 2. And I have a loop that is moving this way. Which of the two is the same and which of them is not the same direction?
Okay, sir, I want to come in.
Please come in.
I think the current 1 or the direction 1 is in opposite to the direction you are giving, and the second one is in the same direction because they are moving in the same.
Does it mean that if
this
one is the same, supposing I trace this one to form a curve, is it going to be opposite or is it going to be the same?
Is the same?
It's going to be the same.
So let's come back to the answer.
So direction 1 is moving in the same direction as what do you call it?
With the
loop.
Yes.
No, I disagree.
And then direction 2 is opposite to.
Opposite.
Please, sir, when you consider the direction 1, you said if you keep on going and you move down, what about if you decide to curve and be going up? Will it be the same?
No, the thing is, we are moving clockwise direction. That is what you have to put in mind. If I move up like this, I'm not moving clockwise.
It's the same direction.
I'm going to move in anti-clockwise direction, and that is totally wrong, right?
Yes.
I'm considering if, say, this one is moving, and I know that my direction is to be moving like to this direction, and I want to move clockwise.
Okay.
It means I'll be going down like this.
Yes.
This one will be going down like this, right?
Okay.
And if I'm at 2, and let's say the 2 wants to be going clockwise direction,
it will be going up.
Is that okay? So now
Yes,
we want to relate this one and this. We want to relate this one here and this.
Okay, sir. Okay, sir.
Now let's go back to the question here. Now, is my I1 going to be moving the same direction or opposite direction?
Same direction, clockwise.
Let's say same direction.
So it's not same, it's opposite.
It's opposite.
So how many people are saying the same direction? How many people are saying opposite direction?
It's the same direction.
So it's the same direction.
If it's clockwise, then it's same direction.
The same direction.
Personally,
I want to give some explanation.
Personally, let me tell you where I stand. Personally, I stand at opposite direction.
Yes.
But if you're able to convince me, I'll follow you. So
I want to
give me your
convince you.
suggestion. Yes, convince me.
So let's consider the loop from our cell up at the top. It gets to F, downwards to junction C, and then moves through, let's say, that resistance 6 ohms. So if you consider that direction, it's opposite to the direction the current one is moving.
Okay.
That is it.
So also have a different view.
Yes, bring it on board, I beg.
From where he is saying, when he moves from there, and then through to the junction C, and then through that resistance 6 ohm, that is moving clockwise direction, and our current I is also moving in clockwise direction. It's also moving clockwise direction. That is why I can say that both are in the same direction.
Now let's look at something here.
Okay.
I understand everyone's submission. In fact, anytime a current is moving and it reaches a junction, it is not the same current again. So let's look at current I2. Current I2 like this. Its movement actually starts from B here. Because all this end here, we don't have any junction here. So current 2 is moving. It moves all the top here. It reaches a junction here. It is not current 2 again. Is that okay? The same way current 1, the movement starts from B here and it goes in a linear manner. So it reaches junction C. It's not when it reaches junction C, it is not current 1 again.
Okay.
Is that okay? Now, when it exits from there, what is happening here is current 3. D here is not a junction, so still have current 3. It will pass through the ohms of 2, pass through the A, and gets to B. When it reaches the junction again, it doesn't belong to its current as current what? I3. Is that okay? So, relating I1 and I2 in clockwise and anti-clockwise, let's be very careful.
Not advisable.
Is that okay?
Yes.
So if that is the case, we know that I1 is moving in a linear manner, and its effectiveness starts from B and it ends at C. It's a linear manner.
Okay.
Now let's look at the direction of the loop that we are considering. is moving in a circular manner like this,
Okay.
is it going to be in opposite direction or the same direction?
Opposite.
The same.
The same direction.
With the current one or
For the
I'm
current
becoming
one, same
convincing.
direction.
With the explanation,
So I think it's
opposite.
opposite direction.
It's going to be opposite direction.
Opposite.
Opposite direction.
it's opposite.
Yeah. Or if with
If
that,
we are talking about
since
current
it's linear,
I2, hold on. If we are talking about current I2, is it
and that
going
will
to be
be
the
in the
same
same
direction
direction.
or opposite direction?
It's going
The
to be the
same
same.
direction.
The same
The
direction.
same.
Perfect. Same direction. So I1 will not be the same direction too. It's going to be opposite direction.
Yes.
Have I managed to convince you or convince you? It's two
I
things.
understood, sir.
I'm convincing
So
you.
it's okay now.
I don't want a situation where you go and stand somewhere and say, oh, Sir Rabbi said, please explain it per your understanding. So let's do all the arguments here. Okay. So I think we are good to continue, right?
Yes, sir.
Perfect.
Yes, sir.
So if that is our justification, and anytime we have a loop that is opposite the current, what happens to the potential difference? Is it going to be positive or negative?
Positive.
Positive.
It's going to be positive. That is
Yes.
what we agree to. Okay. Now let's go through. Now we've settled this situation. We've settled this situation. Now we have another potential difference sitting here. Now let's look at the loop. From the loop, is it traveling from positive to negative or negative to the positive?
Positive to
Negative.
Negative to positive.
It's
No,
negative
from the
to
loop.
positive. Or
So from the loop,
Okay.
it's positive to negative. Yeah, positive to negative. And if we
from
have
the
positive
loop,
to negative, it becomes what?
Negative.
A negative or a positive? A
Negative.
negative. Oh, perfect. So negative 10. It's left is the last one. Because there's another resistance sitting here. We have to tackle all the components in the loop. The last resistance here is 4 ohms. And the 4 ohms, which current is passing through these 4 ohms? Yes, Olo. Which current is passing through these 4 ohms?
I2, please.
Come again.
I2.
I2, perfect. And now I2, comparing I2 direction movement and loop 1, is it the same direction or opposite direction?
The same
same.
direction.
The same direction. So if it's the same direction, what is going to happen to the sign?
Negative.
It's going to be negative.
Yeah.
I am writing what you are telling me. Are you sure? Or we should go back and confirm?
Yeah, yes, please.
I made you write these things down. So please, let's write these things down. So this is the opposite direction. If the current is moving this way, is that okay? And the loop is also moving this way, it means they are what? In their opposite direction. And we have our potential difference to be positive. Is that okay? Now, in a situation where we have it this way, they are all moving in the same direction. And we have it to be what? To be negative. Is that okay? So now let's go back. what is going to happen to this, the I2? Positive or negative? The way no one is responding, are we confused or what?
It's positive.
It will be positive.
Okay, it's going to be positive.
Positive.
If this one is going to be positive, it means what you told me here is wrong. So if we have positive here, it means that our I2 is going to multiply the 4 here, right? So we get 4 I2. Yeah, Madam Priscilla, your hands is up.
We said that the I2 is in the same direction. So if it is in the same direction, then it's negative or not positive. I don't know if I'm also getting confused there. If they are in the same direction with the loop, then it shouldn't be positive, but rather it should be negative.
So let me show you what I wrote here. So if the resistor is transverse in a direction that is opposite the current, then it means that our formula is going to be positive. If it's opposite the current. Now, the situation that we have here, is it opposite or the same?
It's opposite.
It's opposite or is the same?
So, the voltage and the
which one?
the I2.
I'm talking about the I2.
It's the same.
It's the same. So it means we have to get this one to be what? Positive or negative?
Negative.
That would be negative.
This is very confusing.
No, don't let it confuse you. It's very easy. Just follow. So I've changed it to negative. And we equate this whole thing to be 0. So this is going to be our equation 2. Is that okay? So the summation of all the potential difference is supposed to be what? 0. And for us to get the potential difference, that is what we've just done. Is that okay? And for you to get something like this, it depends on the number of components you have there. We have one potential difference here. We have another potential difference here that we can derive from the ohms and the I. We have another potential difference we can derive. We have another potential difference we can derive. Is that okay? So when you look at, that is how we managed to get 4 terms here. When you look at the one down here, how many terms do you think we are going to get here? 3. We are going to get 3. Perfect. Is that okay? So I have derived the equation 1 for you, equation 2 for you. Try equation 3 and let me see. From your understanding so far. Yes, I said Jonathan.
Okay, so the loop is 10 minus 6 I1 minus 2I3 is equal to 0.
Okay, hold on. So can you say it again for me?
Okay, so 10 minus 6I1.
Minus 6I1.
Yes, please. Minus 2I3.
Minus
2I3
I3.
is equal to 0.
It's equal to 0. Okay. Any different submission, or we are all confused?
I had the same.
Oh, okay. You
I
said
also
0.
had the same.
Those who are saying they had the same, are you sure?
Yes, I had the same. The same.
Okay.
Sir, please, I have a question.
Yes, ask your question, I beg.
Please, let's go back to the equation 2.
The what?
The minus 10 over there. I'm thinking it should be positive.
Okay. Why?
We have a current moving from negative to positive, and considering the loop.
No, so when we are considering the potential difference like this, we don't consider the current. We just consider the positive and the negative of the potential difference.
Okay.
You understand? So
yes.
We only consider current when we are talking about the resistance. The current passing through the resistance will give us the potential difference. And in fact, all the terms that we have here, the individual terms, they represent a potential difference. They all will get a unit of volts, because this one is representing a volt here. When we want to find a volt, is V equals IR. We have our R as 6. We have I here. So it represents a volt. This one represents a volt. This one represents a volt. Is that okay? So independent, if we are considering the potential difference, current doesn't play a role here. It's only when you are considering the resistance. Any questions so far?
Hey, that's more question.
Yes, please ask.
Same on equation 2. The 10 volt. The 10 volt today. When we had the negative thing, you said that direction of the loop is moving from positive to negative. So that is what you said. Okay.
Yes.
So is it not me? I was just seeing it from, I'll count it from the negative to positive.
Why?
Or because per what you gave us, that when you are moving from negative to positive, you are positive. When you are moving from positive to negative, you are negative. So I was just looking at it from the negative to the positive side instead.
If we are moving from the law, let me go back. From the law, yes, it. If the loop is moving from negative to positive, it becomes a positive.
Exactly.
If it becomes a positive to negative, it becomes a negative.
Sure.
Right?
Yes.
So now
it's supposed to be positive thing.
Now if we come back here, it means that here we are moving from positive to what? To negative.
Okay.
Okay, is that okay?
No. Okay.
So because look at the loop, it goes this way. So we reach here.
They'll just pass the positive before getting to the.
Very, very, very good.
Okay.
So it means even this one that you have done, we have to go through this one. So can someone help me understand how they managed to get the equation there?
Okay, so equation 3 we are taking the loop BCDA.
Okay.
Okay, moving in the clockwise direction.
Okay.
So
Sir Jonathan, hold on. Please, let's all listen to him, because if you don't understand, maybe this explanation will help you understand. I beg of you. Okay, so let's continue.
Okay, so we are moving from B. So when we start from B, we'll get to the cell, with the 10-volt cell. We'll first meet the negative term now before the positive term now. Okay, so our negative positive is in line with the rule that says that when the loop moves from negative to positive, then you are going to get a voltage gain. So the voltage will be positive. Can I continue?
Yes, perfect. It's fine. Continue.
Okay. So from there, then we will now meet the 6 ohms resistor. So as we can see, the direction of current I1 is also in the same direction. That's from B to C, just as we are moving along the loop. Okay, so the rule says that when the current and the loop are moving in the same direction, then you are going to have a voltage drop. So your current will be negative. Okay, so looking for using Ohm's law, voltage is equal to IR. It means that we are going to multiply 6 by I1, and it's also negative. So that's why we have the negative 6 I1.
Okay. Please, are we all okay?
Yes.
Perfect.
Okay.
But sir, I have.
Now we get.
Sir Jonathan, hold on. Yes.
I have a question.
Please ask.
I want to ask Ketchup a question. That did he just told us that moving from positive to negative is negative EMF, and vice versa, as he did to the resistors too? What did he do? Did he calculate something, or he just
This question there, I think.
Let's get it.
So who will help me answer this, because I don't have an answer for this.
My man of Kitchens in the number no contact no friend.
Okay, I got you.
Sir Jonathan, let's go on.
Okay, thank you, sir. So now we are junction C or point C, moving downwards to D. Okay, so the current from C to D is I3, and that's the same current that is passing through the 2 ohms resistor. Okay, so the direction of the current and the direction of our loop clockwise movement are in line again. So there's going to be a voltage drop in the 2 ohms resistor, and so that's why it's also negative 2 I3. So all this put together should be equal to 0, and so we equate it to 0. Thank you.
Right. Okay, that is perfect. Any questions so far? And after deriving these 3 equations, the only thing left is simultaneous equation, and I'm sure we remember simultaneous equation. Madam Presla.
My question is, do we always consider the V first before we consider the I and the R?
Oh, no. In fact, we can consider any of them. At the end of the day, it's still going to be the same equation. But we are starting from the easiest one, that's why. Because the V is easy to determine it.
Okay.
Anyhow you do, the equation will still be fine. Is that okay?
Okay, sir.
Now
Hey.
let's look at something here. In fact, after doing change of subjects and do we remember simultaneous equation?
Yes.
This change in equations and subjects that we do. So you can make I3 the subject, come and put this one in, and you can even simplify this equation more, like the one that Jonathan gave us. In fact, what we have there is the same as 6. Let me know, right? It's the same as 6I1 plus 2I3 equals 10. Is that okay? Because if this one goes here, then we cancel all the negatives. It's still going to be like that. Is that okay? We can even deduce it because we can divide 2 through so that we get I3 plus 3I1 equals 5. Is that okay? So you can just be reducing it and making it very simple for your calculation. Are we a little bit okay?
Yes, sir.
Very good. So getting the answer is going to be our assignment again. So you have to find for I1 for me, I2 for me, and I3. And please, if you get the time, go through the second equation or circuit diagram for me. Is that okay? This one we are finding for I1, I2, and I3. I beg of you. I think I have some equations here. I derived this thing here, so it's supposed to be the answer. So when you finish, you can compare this one with the very first one that we just did. Is that okay? And the second one too is here. And we are done with what we're supposed to finish last week. So we are now coming to do the third week's point. That is optics. I think I have some hands up.
Please, I beg of you, can you just go back so that I want to write the equations there?
No, I've shared the slides. Oh.
No, I mean what you were using the pen to write.
Okay.
Okay, thank you.
So you can just do a screenshot.
Yeah, okay, it's okay, thank you.
Now we are done with electric current, and now we are going to optics. Is that okay? So maybe from this end, if you can mute yourself so that I'll talk a little. Then, if you have a question, raise your hands and I'll continue.
Yeah, no break.
Now you'll be looking at waves one way, the other. Then you will look at a little bit of physical optics. Is that okay? The very, very basic ones. And all these things that you are coming to talk about, you are familiar with it one way, the other. Is that okay?
Please, let's go for break.
We should go for break. Oh, okay. Sorry. So how many minutes do you want us to go for break? 10 minutes?
5 minutes.
5 minutes.
5 minutes is too short. Maybe 10 minutes is fine. Is that okay?
Okay. So because of our time, the time is too limited for us.
Yeah, let's be just 1 hour 30 minutes.
There's a lot of things for us to cover.
Yeah, don't worry, 10 minutes is fine. 5 minutes, it will just come. So let's charge our phone exactly after that 10 minutes. When it's 10 minutes, I'm starting. Is that okay? So please, when it's 2:40, I am starting this up. I beg of you. So I'll be online waiting.
Okay.
Thank you, sir.
Jonathan, let's meet outside.
Hello, sir. And are you on break?
Yeah, we are on break.
Hey,
10 minutes.
10 minutes. All right.
Okay. Can we start? The 10 minutes is up. Okay, so we are going to look at optics, and what we have here, they are not that much. In fact, most of the things here you've seen or you've read between it one way or the other. Exactly. So it's going to be a very quick recap. Then I'm just hoping that we can finish. So the very basic optics, when you're talking about the direction in which light moves, in optics, we use just a straight line and an arrow at the middle to represent it. Is that okay? So it's very important. So anytime you see a straight line and an arrow, it's telling us that light is moving in this direction. We don't place the arrow at the tip here as I have here. This is wrong. Is that okay? So the arrow is placed at the middle. Is that okay? Now, if we have 2 or more of these arrows, it is called a beam, and it's not placed like this. We place it at the middle here. Is that okay? So we have this one as a beam. And in fact, the beam movement is very dependent. When I say it's very dependent, in fact, we can have a beam going very straight and never meet. So something like that, we call it a parallel beam. And a very typical example is what I have here. And we can have another one that the beam is at a particular point and it's moving out. So you see, let's say the light is here and it's actually moving out like this. And here we call it a what? A diverging beam. Is that okay? It's moving out. But what if the beam is actually meeting together at a particular point? Here we are saying it's converging. Is that okay? So it's a converging beam. And we use converging in even English language. We say, let's all converge here when it's 2 o'clock to have a discussion. So wherever we are, we have to come and meet there. Is that okay? So that is a converging beam. After the meeting, we say, oh, then we can all diverge. And we can all go to our separate ways. Is that okay? So that is it for the rays and the beam. And in fact, when it comes to this direction in the movement, we have a particular property we call the reflection. And under reflection, we have a particular famous law that we call as this one, where we say the incident ray, the reflected ray, and the normal, the point of incident, all lies on the same plane mirror. Is that okay? And I think I didn't mention, this thing is very important to the extent that even when we are teaching the kids in the elementary as we do, we tell them that light travels in a straight line. And in a way of even doing this, we have some candle or a light and we place some cardboards with a hole at the center to let them know that, of course, light can travel or it do travel in a straight line, which we'll be talking about it later. Is that okay? So that is for reflection. And when we are drawing a schematic to represent this one, we have an incident ray and we have the reflected ray. And in between the incident and the reflected, there's something we call the normal in between. And they all lie on the same plane. Is that okay? So the most important takeaway when it comes to law of reflection is the angle of incident and angle of reflection, which of course they are supposed to be always what? Equal. So it means if we have 20 here, this is supposed to be 20. If you have 90 here, this is supposed to be 90. But let me ask the class a question. If we have this 20 here, what will be the angle here?
70.
70.
70.
Perfect.
70 degrees.
Okay. Perfect. Because the normal is what? Perpendicular to the what? To the plane. So that is it for reflection. And under the reflection, we have something we call specular or regular and diffuse or irregular reflection. In fact, there are some surfaces that they are not as smooth as you see. Even your mirror, they are not very smooth. They have a microscopic surface which is very irregular. Is that okay? So some of our mirrors, some of them even behaves as this. Is that okay? If you want a specular one, a very typical one is the mirrors that we have in the lab or something. And that one we are talking about 97, 98, 96% of reflection. Very, very effective. And what we are saying is here is anytime we have a specular reflection, we should be expecting a parallel beam hitting the surface and the same parallel beam exiting the surface. Is that okay? So when you look at this one, we have our beam here, beam 1, beam 2, ray 1, ray 2, ray 3, all forming a beam. Right after hitting, at the same angle, they all exit. Is that okay? Which is very important. But for the irregular, it doesn't happen like that. In fact, we may get the same beam. That is what? Entering. You see, they are all parallel. But when they are about exiting, it will not behave as parallel. Look at where this one is. It's not parallel to what we have here. And in fact, it's not even parallel to what we have here. And it's not also parallel to what we have here. That is the basic difference. And the reason being that the surface here is not what? It's not smooth. It's very, very rough. So the normal of this one is going to be different from the normal of this one. And it's going to be different from the normal of this one. And it's going to be different from the normal of this one. Is that okay? But let me ask the class a question. In a situation like this, do we still have the law of reflection to be obeyed here? That is I equals R.
No.
Okay.
Yes, it will be.
Okay.
It still obey the laws of reflection.
Okay.
No, doesn't obey.
It can be equal.
Okay.
Please,
Can we justify ourselves? Yes, please, those who are saying no and yes, can you help me understand?
Okay.
I want to come in.
Please come in.
Looking at the angle of incidence, the rays, they are not parallel, meaning they are not meeting. The same applies. I'm talking about the smooth surface. The same applies to the angle of reflection. They are also not parallel, meaning they are not meeting. But when it comes to the other side, the angle of incidence, you can see three of them. The rays, three of them are parallel, but the reflection, they are crossing each other, meaning they are meeting. So the angle of incidence is not the same as the angle of reflection when it comes to the rough surface.
That's the diffuse reflection. Okay. So please, those who are saying yes, can you justify? Can you help me here? Oh, I heard a lot of yeses. So what happened?
Yes, please. You see, looking at the rough and diffuse reflection, the first one and the second one, they are the same, but when we move forward, the other ones are not the same. So some are the same, some are not the same.
But do we understand? Okay, sir, thank you. Do we understand when we say I is equal to R? Do we understand that phenomenon?
Yes, sir.
Yes, sir.
Very good. It means that we have a plane surface like this, and I is hitting the surface. Yeah, someone wants to talk.
I also think that the law still holds no matter the surface.
Correct.
Explain.
Yeah, me too.
Okay.
Benjamin, come and explain for us. Benjamin.
The only thing that changes is the direction, but the angle of incidence is still the same as the reflection. Angle of reflection.
Okay.
Yeah, we are listening. Benjamin.
I think my man has said something, please.
If we have a very smooth surface, and this one reflects, we're expecting our normal to be around this end. That is very, very perpendicular, if it's possible. Is that okay?
Yes.
But in a situation where we have a very small, rough surface a little, we still have our incidents coming. But this time around, after hitting, because it's not a smooth surface, our normal is not going to be perpendicular. The normal may be even facing this end here. So we get our incidents coming, and at the end of the day, our reflection may even pass here. Now, the answer is yes. This one still holds in a situation like this. Is that okay? The situation being that this one is a very smooth surface, and we expect all of them should have a normal to be the same, that is perpendicular to the what? To the surface. So if they all have the same normal to be perpendicular to the surface, of course, the beam that we are expecting to hit the surface, that is parallel, we get the same beam exiting, that is also parallel. It makes sense. Now here, the surface is very, very rough, sorry. Now, because of its roughness, the normal that we are expecting from individual ones is going to change. So if you look at the last one that I've drawn here, the incident angle is coming this way. It hits the surface. Because of the roughness here, it reflects to this angle and we get our normal here. But what we have to put in mind is whatever the situation, this still holds. Because at the end of the day, if I take this ray, it hits the surface, it reflects. My I here should be the same as my R here. If I take the second ray, it hits the surface. My I here should be the same as what? My R here. If I take another one, this one, it hits the surface. My I here should be the same as my R here. The last ray, my I here should be the same as what? My R here. The only thing it is changing is the normal because of its roughness. It changes the angle of the normal. It will make the ray coming have a different angle of reflection. But what we have to put in mind is whatever being the case, this still holds. And in fact, it's even a law of reflection. What examples that we are giving here are types of these reflections, which is still under reflection and has to obey that law. Have I managed to convince you a little?
Yes, sir.
Perfect.
Yes, sir. Yes.
Okay. So now let's go on. So that is the two types of reflection. Someone can say specular or diffused. Another person can say, oh, we have regular and irregular. I'm fine. But please don't go and say specular and regular reflection. No, they are all the same. Is that okay? So either of them, you take one here, you take one here. Now let's look at this. For a plane mirror, we expect that anytime we stand in front, there should be something happening. If we have an observer here, and this is our object, we expect that the incident light comes here and the reflected comes here. And of course, this is our point of what? Incidence. And we get another image behind. Is that okay? This kind of image form has its own properties. And I'm sure you are very familiar with this. The first property is they are upright. Is that okay? And what is the opposite of upright when you are talking about, say,
Inverted.
Inverted.
Perfect. And the next thing is, for a plane mirror, we expect it to be what? Virtual, which I'll be explaining later. But anyways, what is the opposite of virtual image?
Real.
Raw image.
Real.
Perfect. Then the next thing is, we expect it to be the what? The same size as the object. So we don't expect that me that I have a big head, when I stand in front of a mirror, my head should shrink and go down. It's supposed to be big as I have. Is that okay? So if you stand in front of a mirror and it changes the size of you, it means that it's not a clear mirror. Is that okay? It's either a convex mirror or a concave mirror, which we'll be talking about later. So whatever be the case, we expect it to what? The same size as the what? As the object. That is for the image form. And the last thing is, it should be literally what? Inverted. And do we understand this English?
Yes.
Have we heard it before? Yeah, what's the meaning? Can someone help me?
Upside down.
No.
Hello.
It means
Turn sideways.
If you face it, it will also face you.
You face it, it also face what?
When you watch the mirror, you always
Opposite.
pick up your right.
The right turn to the left and the left turn to right.
Perfect. Is that okay? So when you stand in front of your mirror and you raise your right hand, our
You see it as
supposed
11
right
as your
inside
left.
the mirror, that is our image, is going to be the opposite of it. So you raise your hands, you see that the opposite hand rather raises up. And if you raise your left hand, the opposite hand rather raises up. It's not a direct hand facing you in the mirror that is going to raise up. Is that okay? That is what's literally inverted. So let's keep these things in mind. I have a question for the class. Okay. This one, we can just look at it and answer. What will be the answer for A? A ray of light strikes a mirror at an angle of 53 to the normal. What will be the angle of reflection?
53 degrees.
What is the angle between the incident and the reflected ray?
106 degrees.
106 degrees of it. Let's go on. I have another set for the class, but this one I prefer you do it yourself. Is that okay? So that I'll try and see if I can beat time. But just go through. If you have any question, the next time you meet, then you bring it up. Now, images can be in two forms.
Hello, sir, please, can you go back to I take a screenshot of the question?
Come again.
Please, can you go back to the previous slide so I take a screenshot?
Oh, you have the slides, or?
Yeah, we have them.
Yeah, it's in the slides.
Yeah, it's in the slides. I have everything in the slides. I've not updated anything. Is that okay?
Thank you.
When it comes to images, we have two types. The first one, we call it a raw image, and the second one, we call it a virtual image. In fact, these two things are very important. When you're talking about raw image, we are talking about the actual intersection of light rays, which you've heard before. Is that okay? And one is the apparent intersection of light, which you've heard before. But the most important thing that I want you to know when it comes to real image and virtual images, the raw image can form on a screen. In fact, I can even put an image on my palm. It's like going to use a projector to teach students. You need a screen before you can put the image on. We can decide that we don't want a screen. Then you bring one of the students' dress, hang your dress, and let's put the image on. Is that okay? And you start teaching. Is that okay? That is a raw image. But virtual image is inside something. There's no way you can project a virtual image somewhere. Is that okay? And a very typical example is what I have here. We have a candle here. That is our object, and we have a lens here. And this is our image. Is that okay? It is formed behind and on a screen. He can decide to put this image on his palm, which is very possible. Is that okay? And we call this one like a raw image. A virtual image, look at this kind of image formed. It's formed inside the lens here. It's not on the screen. Is that okay? So this is a typical virtual image. So if you are watching something or you are listening to me and watching my slides on your phone, is it a raw image or a virtual image?
It's a virtual image.
Virtual. A virtual image. If you are going to teach and you use a telejector to go and teach, is it the image you are getting, is it a virtual image or a real image?
So far as this image, it's a virtual. Unless it is rare-handed, they can handle it, they can feel it. That becomes a real image.
No, you see a projector, telejector. You send it to class to go and teach. You have your laptop. You connect it to a projector.
It's a real
image.
It's a real image.
It's a raw image.
Yeah.
Yeah, because
for a projector, you need a screen before you can project on that screen. Is that okay?
Yes, sir.
That is why I'm giving you an example that we can decide that we don't want that screen and we bring a cloth. Like virtual image, you have that flexibility to put the image anywhere that you want. That is what I want you to understand. Is that okay? Virtual image, you don't have an option to that. Where it is there. You can't do anything about it. Your phone or your laptop, you are watching the slides on. You can't say you want it on top of your wall, like your room wall should be on it. No, you don't have that flexibility. It is formed in there. That is all. Is that okay? But the raw image, you have that option. You can put the image on your room wall. Oh, today I don't want to watch it in the room. You send it to your hall or your veranda or your kitchen. Put the image on it. You can watch antenna or kunkumbajia or anything, football in your kitchen on the kitchen wall. Today I don't want to watch it there. You send it to the and it's not a TV that we are talking about. We are talking about the image itself. Is that okay? That is the kind of image we are talking about now. Okay. So it's very important to know that. That is why right now we have something like the virtual display screens. You see, Apple too, they do have some, and Meta too have some. That screen they put it like a lens, a big one on their eyes. Then they can look at it. They even use it to play video games and other things. Is that okay? That one is a virtual display. It's called virtual reality something. Is that okay? And that one helps you to also. It's also still a virtual image. It's inside there. You can't project it anywhere unless you wear it and you see it inside there. Is that okay? Which they've coupled a lot of lenses in there. Now, if we understand virtual and raw image, let's talk about Snell's law.
They say.
Yes, sir.
For the virtual and real image in one sentence, or can you wrap it again for us, especially me?
Can someone help me here?
So I want to put a question across to maybe even will help me to understand, because I'm also getting a bit lost with the virtual and the real image.
Now, right now, I need a help. And Stephen, you are asking another problem.
No.
I can say that for rare image, it can be formed on a screen, but virtual image cannot be formed on a screen. And the second thought is that for virtual image, you cannot, because it's not formed on the screen, you cannot change the type of screen that you want it to be on. But for rare image, maybe you don't want a wall as a screen, you can use the ground as a screen or any other screen that you want.
Even again, for the rare image, for example, a camera, it can be formed on the screen. But when it comes to the mirror, it is virtual because the image, you will see it to be behind the mirror. It is not on the screen as it's on the camera.
Okay. So how should I explain this? Okay, so let's look at what I have. I have here. You see, I have a raw image here, and I have a virtual image here. And you see, if I have a candle here, I have a lens here, and it forms an image behind here. It's the same candle that is here. But this candle, where you want it to be formed, you have the flexibility.
Okay.
You can actually remove the background here and even put a red background, and it will form there for you.
Okay.
You can remove this background and put your hands there. The image of the candle will be formed there. That is the image of the candle. Okay. But the same image of a candle in a lens, look at how it looks like. Whatever being the situation, is inside here. You can't let it form in your palm. You can't bring a screen that of your choice to put it on. Is that okay? It's inside the lens. Is that okay? Right. You can't say I want my image on the wall. You don't have that flexibility. Is that okay? And that is what we are calling a virtual image. And here it's not something that is printed like a picture hard copy. Is that okay? It's a different thing that we are talking about here. So here we are talking about the fact that we have an image that is raw. You see, you can talk about raw to say nipa raw human being you are touching, kind of. And the virtual is something that is presumed, kind of. So this one is an image we can actually let it be touched, or let's say form on our screen, or that anything that we want of our choice. Virtual is not like that. It's formed inside something there. Is that okay?
Okay.
Yes, this one, your hands is out.
Yeah, so can you say that the image found on a thin mirror is a real image?
Can you let your image be formed on a screen or
No.
anything that you want?
As in, so
So so let me say this one again. A typical example of image formed with a mirror is a virtual image. Is that okay?
all right.
Yes, sir.
So it is formed behind that mirror.
Okay.
What we are talking about here, okay, I'm coming. Let me show you. Did I add this? No, okay. Please kindly hold on. I want to show you something. Please hold on. I'll come to you. I'm trying to show you something here. So, Mr. Buff, I'm coming. Okay. Can you see something?
Yes, please.
Yes, sir.
Yes, sir.
So, have you seen a projection like this before?
Yes.
Yes.
Where they use a projector or a teledetector like this. Have you seen something like that before? Or have you seen
Yes.
some people use a cinema and watch something like this? So, this kind of image from here, is it a raw image or is a virtual image?
A real image.
Real image.
It's raw image. The person can remove this thing and they will say we don't want to watch it in the room today. They will go to their hall or anywhere and go and watch it there. Is that okay? This, you need a screen before you can watch it. Is that okay? But when you take a mirror, your image is formed.
Yes, sir.
Is someone trying to talk? Is that okay? But when you
Yes,
take
sir.
something like, is someone trying to talk?
No.
Okay. But when you take something like what I have here, this is a TV. This is not formed on a screen. Is that okay? So something like this is a virtual image. When you take something like this, you need a screen, like a whiteboard, to place it there before you can get that kind of an image. Is it a little bit better?
I think I now understand, because that's the question I had wanted to ask.
Okay. So now, if that is the case, let me stop presenting present the slides. Yeah, sir, Mr. Boafo, I'm listening.
I saw something somewhere else. Can I read so that we'll all hear it?
Sure, sir.
Okay. The difference between real image and virtual image. Example, when you watch a movie in a cinema, the picture on the screen is a real image because the projector's light rays meet on the screen to form it. Then the other example, when you look at yourself in a mirror, you see a virtual image because the light rays from your face only seem to come from behind the mirror, but they do not actually go there. So that's the example that I saw somewhere else.
Mr. Boafo, explain it to us. The English is long.
So I saw it somewhere else, so I was just trying to read it to the hearing of the class. Maybe if someone can also help me.
Oh, I did not. Anyways, Mr. Boafo. Anyways.
Sir Rabi.
Yes, sir.
So from your examples or the results that you just put displayed on the screen, we can also say that the image found on the driving mirror is an example of virtual image, right?
Perfect.
All right.
Hello, sir.
Yes, sir.
Please let me try to explain what my senior man said earlier.
Okay.
In this direction, if we should use the projector, you could see that there are light rays coming out of the projector and meeting of those light rays on a screen that is forming an image. And that image is real because it's the intersection of what? Light rays. Please, are you following? Or I'm confusing you rather.
Oh, you are following.
Yes. Now, if you look at yourself in a mirror, the reason why it is a virtual image because the image tends to form behind the mirror, not on on the real mirror, but it looks as if it's formed behind the mirror, and that is where the virtual or virtuality comes in. I don't know if I've confused you the more or I've tried to explain myself. Thank you.
Okay, perfect. Sir Jesus, thank you very much. Okay, so now let's go on to Snell's law. Are we a little bit okay with the raw and virtual image?
Yes, sir. Yes, please.
So Snell did a lot of work when it comes to this refraction. So we were having reflection, then this man observed a lot of things. The first thing that he observed is if he placed, say, a pencil in water, he tends to observe that the pencil bends a bit in the water. That was a very nice observation. Another thing that he observed is if we have light, like a flashlight or torch, that is traveling in air, immediately it enters into a medium like water, it will move very slowly. Before that, they were confused. Could it be that there are some chemical reaction going on there that reduces it? But interestingly, when it exits, it goes fast again as it were before. Is that okay? So which was a very nice observation as at that time. And that was how the birth of refraction actually came in place. And what we are talking about here is the bending of light rays. And the bending of light rays is because of the densities of these two mediums. Under refraction, we need two medias at hand that is having different densities or different refractive indexes. Is that okay? So let's say we have two medium like air and water. Air, of course, water is going to be more dense than air. we expect that when light is traveling from the air and it's about hitting the surface of this one, from our reflection, we know that the normal is going to be here. Supposing this one is a plane surface, we're expecting reflection to go back here. But this is not a plane surface. It's a different medium is hitting. So it will enter. A different medium that is transparent. Let me say it that way. Is that okay? So it will enter. But interestingly, because it's entering a more dense medium, ideally, if it enters, why don't it go straight like this? But because it's entering more dense medium, it will tend to bend a little closer to the normal that we have here. Is that okay? And this is what our refracted ray. Is that okay? So whatever being the case, there's going to be a bend as far as we are traveling from a dense medium to another medium, or a less dense medium to another medium. Is that okay? But let's look at the reverse way. This is from a less dense medium to a denser medium. What if you are traveling from a denser medium to a less dense medium? Now, let's imagine ourselves underwater or a pool. When now we are traveling from under the water, you are here. With a torch. So ideally, when it hits the surface here, we expect it to reflect. But it doesn't happen like that because we are talking about refraction here and the medium is transparent. So it will exit. But even after exiting from this end, we expect it to travel straight as this. But it doesn't happen that way. It bends away from the normal. Is that okay? And this becomes our angle of what? Refraction. And here is because we are traveling from a denser medium to a less dense medium. Here we are traveling from a less dense medium to a more dense. Is that okay? Some people, they will say a rarer medium to a dense medium, and that as such, that is fine. So these observations were very important. And it's because of this observation that we're able to find the refractive indices and other things. In fact, Snell derived a law under this. And there's a particular interesting formula for finding the refractive index. So anytime you hear the word refractive index, refractive index, refractive index, it is through the observation that Snell did. The observation that we are talking that light traveling very fast in air and entering into water or a dense medium, traveling very slow, and exiting, traveling very fast again. Is that okay? And the refractive index is just telling us that if you have a speed of light, what is the speed of light anyways? The unit, oh no, the value for the speed of light.
3.0 times 10 raised to the power 8 meters per second.
Okay, so that is in a vacuum. So if you have the speed of light, say in a vacuum or in air, and we use the same light to pass through a medium, say water, and we get the value here, we can find the refractive index of that water. Supposing it's not a water, it's a glass prism, glass block. Then we find this, we know the speed of light of air or vacuum. That is the 3.10 to the power 8 you said. Then we find the speed that is traveling in the block. It means that we can find the refractive index of the glass block. Is that okay? Now let's look at something. What if we are not using the speed of light? There's also another way. And here we can use the what? The wavelength particularly. Is that okay? Of the two. We can find the wavelength of light traveling through the air and the wavelength of light traveling through the medium. Is that okay? So either this or this, we are good to go. So now, with the two of us, we know that we have two formulas for refractive index. The first one using the speed of light, that is the velocity, and the second one using the wavelength. So Snell, of course, brought his law, and it is the same as what we have with the refraction also having its law. But the most important one that has been we're working with is the second one. And mathematically, we write it as N1 sine I1 equals N2 sine sine R. Sorry, N1 sine I equals N2 sine R. And here we are talking about one medium here, and we're talking about another medium here. So the N here is representing the refractive index of that first medium and the incident angle of that first medium, and the refractive index of the second medium and the incident angle, the refracted angle of the second medium. Let me go back and show you. So a situation like this, we are talking about N1 here as the one at the top here, and the down here is going to be what? N2.
N2.
And we have our I here, we have our R here. Is that okay? So the sine N1 sine I here, N2 sine R here. Is that okay? That is what is giving us this mathematical expression. But as and now, the two of us, we know that if I have N is also the same as what? C over what? C over what? Can someone help me?
C over V.
C over V. What I just shown you here. So N equals C over V. If we insert this formula into these terms, it means we are going to get our N is going to go off. Then I'm going to get C on what? V1. Do you agree to that?
Sure.
Our N2 here goes off, and we get C on what? N2. C is common here, C is common here, so we cancel it. At the end of the day, we get 1 over V1. That is what is here. Sine I equals what? 1 over N2, V2 sine what? R, or the theta 2, exactly, which is the same. So if the question don't necessarily gives you the refractive index and you have the speed of light, you can still find the angles. Supposing you're asked to find the incident angle, you should be able to calculate the incident angle. Supposing you're asked to find the refracted angle, you're supposed to be able to find it. Suppose you're asked to find the refractive index, you're supposed to be able to do it. The velocity, you're supposed to be able to do it. Just change of subject. Now there's a question here. I'll bring this question up, but let's hold on. Now, under refraction, there's one important phenomenon. We call it total internal reflection. How many of us have heard of this before? Before I go on. Okay. Can someone tell me a very typical application of total internal reflection? A very, very typical application of total internal reflection. Yes, Azuma.
Okay. What I would say is that whenever you are on a road, the tar road, and you are moving, whether you are in a vehicle or in a construction, and you look far away from the, you look far away. It will look as on the road. Yeah, there is water. It's like a pool of water lying down on the road. So I think that's where the internal reflection takes place. Meanwhile, and get to that place, you will realize that it is not water.
Okay, Sir Philip. Okay, Sir Azuma, thank you.
I think in the fiber optics for wave transmission.
Okay, how does that work in fiber optics?
It's a continuous reflection throughout the fiber.
Perfect. Then what again? Do you have another hands? Okay, so let's go through briefly. Now, supposing a light is traveling from a denser medium, no, let me say it this way. Supposing light is traveling from a less dense medium to a more dense medium, is the refracted ray going to bend closer to the normal or away from the normal?
Away from the normal.
No, relax and let's listen. If we have light traveling from a less dense medium or a rarer medium, less dense medium, to a more dense medium, like say from air to water, will the refracted ray bend close to the normal or away?
To bend
It will
towards
bend
the
close to the normal. Perfect. It will bend close to the normal.
Bend away from the normal.
What if we are in water and it's traveling the water that is more dense to air? Will it bend close to the normal or away?
Away.
Away from the normal. Perfect.
It will bend towards the
It is that situation that we are looking at here. Look at the first one. We have a more dense medium and a less dense medium. We are traveling from A to C. So this is our incident ray. Sorry, there's incident angle. This is our refracted angle. Ideally, it's supposed to be going this way, right? But it will bend away from the normal. And of course, we get some small partial reflection. So let's move on to that. But let's look at something here. Supposing I increase the angle of incidence a little, and maybe bring it around this end here. What do you think will happen to the angle of refraction?
It will also move away from the normal.
From the normal.
So it will also increase. It will also move away from them.
Yes. So move to Y.
Okay. Towards the I, towards the Y. Thank you. Now, we can increase the I again. And of course, the angle here will also increase. We can be increasing I to a point where the angle for the R here is on the Y. Is that okay? And at the point where we have the refracted ray on the Y, we call this angle of incidence as what? Critical angle. And at that point, our angle of refraction is what? Is 90 degrees.
90 degrees.
Can you give me a thumbs up if you understand before I move on?
Sir, please, can you go over that one again, please?
Okay. So we are saying that anytime I increase, you see the angle where this one is, it will also increase. When it's increasing, it means this one too is moving away this way. So it will increase a bit. Supposing we increase the I again, this one too will increase. Then we increase it a little bit again. You see that it will go and lie on the Y. So this time around, we have our angle of refraction from this end here to this end here, which is 90 degrees. Is that okay?
Yeah.
So at that point where we have our angle of refraction to be 90 degrees, we don't call the incident angle as incident angle. We call it a what? A critical angle. Is that okay? But even under this situation, supposing we increase the critical angle again, what do you think is going to happen? Any idea?
The reflected angle will be greater than 90 degrees.
Supposing
there will be no
there will be no
reflection.
refraction.
So it will be totally internally reflected.
Thank you. Because anytime we increase the I, R is increasing. So if we increase the I and let it even exceed the critical angle that we have this one as 90, it will not be on the Y again. It will increase and come here. Is that okay? Because anytime we increase this angle is continuously increasing. And anytime we have this angle exceed the Y, it's not refraction we are talking about again. It's reflection we are talking of. Is that okay? So anytime we have the... Yes, sir. Is someone trying to talk?
I don't think so. So
Go ahead, sir.
So anytime we have an angle that is greater than the critical angle, we have what we call the reflection, which is very important. That is why I'm saying that if you have incident angle greater than the critical angle, it's called a what? Is the reflection that we're getting. But if you have incident angle to be equal to what? Critical angle, what is going to happen to the refraction?
90 degrees.
90 degrees. Come again. But if this one is greater than the critical angle, then we call it what? Reflection. And that is what we call the total internal reflection. Is that okay? And this is very important because of this, if a fish is under the sea, through reflection, the fish can know what is actually going on in the sea at the other end. Because if the fish is here, and it's observed from this end, because inside the sea, the water is more dense than the outside one. So it can reflect on the surface inside there, then look at something that is here. Is that okay? If the straight part is not helping. Is that okay? This is very, very important. Now, let's do another thing here. We all remember the Snell's law, right? Now we are bringing Snell's law here. If you do a small change in subject, we bring the N2 down here and we bring the sign I down here, you are going to get this formula. Now, in a situation where we are dealing with water and air, we know the refractive index of air is what? Do we know the refractive index of air?
Yeah.
One. Do we know the refractive index of air?
1.0.
1.0.
That is 1. Is that okay? So if we have the refractive index of, let's say we are traveling from air, between air and water.
1.3.
But air is 1. Is that okay?
Yes.
And we have this formula. And our second medium here, that is the N2. And here is our N1. It means our N2 here is going to be 1. Because this is air and this is more dense. Say water or something down here. Now I want to insert the 1 here. So I'll cancel the N2 and bring 1 here. Now we know that R is 90. So I want to remove the R and bring 90. And that is what I have here. So now I have my N1 over 1. That is the effective index of air. Sine 90, that is the what? The refracted angle. And the sine I. But this time around, this one will not be I, it will be what? It will be C. Critical angle. And I'll get this from the final answer is. So N is equal to what? 1 over sine of the what? Critical angle. Are we okay?
Yes, sir.
Now this thing has a lot of applications, but I'll talk to it out. I'll talk to it later. Let's try and go through this together. So I beg, I'm stepping out briefly. Can we take a screenshot of this? Can we take a screenshot of this?
Yeah, it's taken.
Yes, please.
Then when you finish, let's do the one that we just took a screenshot of, and let's do this one too. I'm coming briefly, 2 minutes. Like.
Light will travel from the air into the water. Refraction. Water. Okay. So the angle of incidence is 34 degrees. What
I beg, any answer for me?
Yeah, the first
What
one.
are we getting for this? The first one. Okay, let's go to the first one. Yeah, what are we getting?
I had 41.1 degrees.
41.1
degrees, the critical angle.
Okay, the critical angle.
Yeah.
What formula did you use here, I beg?
Refractive index, that's N is equal to 1 over sin C.
Mm-hmm.
Yeah, and then I made sin C the subject, and I found 1 over 1.52, and then I did sine inverse.
Okay.
To get the critical angle.
Which you said you had what,
41.1 degrees.
41.1 degrees. Are we all getting the same thing, I beg?
Yes.
Yes, sir.
Okay. So let's go to this question. What are we getting for the first one? We are given the incident angle.
For
We are
the
asked to
first
find the
one,
angle of
that's
the
the
refraction.
angle of refraction. I got 24.9 degrees.
Can you guide me through how you managed to get that?
So for the formula, which is N1 is equal to sine theta 1 equals, that's the A equals N psi, which is the reflection angle.
So hold on. So N1 sine
I.
equals N2. Sorry about my writing. I'm missing the bounce part, so it's very difficult to write with it. Are we talking about this formula?
Yes, sir.
Perfect. So here our N1 is what? We are
So the
asked to find
N1
for
is the
what?
air,
Okay, N1 is the air.
and the N2 is the water.
N2 is the water. And here, what are we looking for?
You are looking for the angle of reflection, which is the theta 2.
Theta 2, perfect. And the N2, what is the value for the N2?
For the N2, for the value for N2 is 1.33. That is in water. And that of air is 1.0.
Okay. Can you take us through the arrangement and how you managed to get your answer?
So you just, where there is N1 and N2, you place the N1 with 1.0 and that of the N2 with 1.33. So you are going to get 1.0 sine, that's theta 1. Theta 1 is the angle of incidence, that is 34 degrees. So you're going to get 1.0 with sine 34 equals 1.3 sine, that's theta 2, the angle of reflection. And
perfect. So what are we getting?
after doing all that, I got the final answer to be 24.9.
I beg, are we all getting the same thing?
Yes, sir.
Yes, sir.
Great. Can another person help me with the last one, please? Hello. Can I get help with the second question?
We are coming.
Oh, no one is able to do it. What is going on?
We are doing it.
Okay.
So
Yeah, I'm here.
yeah, I had 1.99 times 10 exponent 8 meters per second.
That's correct.
Okay. 1 point.
Yeah.
Uh,
99 times 10 to the power 8 meters per second.
okay,
So
can you guide
approximately.
me how you managed to get it?
I use the Snell's law,
Mm-hmm.
which is the refractive index was speed of light in air, which is the c, over the speed of light in the medium, which is the v.
Mm-hmm.
So I had n equals c over v. Then there I made v the subject, which is the speed of light in the medium, which is the chloroform we are looking for. So it now
Yeah.
became v equals c over n. And we know the speed of light
Okay.
in air, which is c, to always be 3.0 times 10 exponent 8 over that. The
Okay.
refractive index is given to be 1.51. So I computed and had 1.99 times 10 exponent 8.
Please, are we all understanding?
Yes, sir.
Yes.
I think so.
Yes.
You are going to leave your answer as 2.0 times 10 to the power 8.
0.0, or
Are
you're
we
getting
getting
1
to?
point something?
I'm getting the same 1 point. I'm getting one.
It's 1.99.
Yeah, I'm getting 1.99. Yeah. So the same thing.
I don't
Okay.
think it's right for you to run it to 2.0. And I said,
Okay. So I'm saying that because if you check the speed of light and then the speed of other media, you can see how, if I'm right, you can see how the answer their value is.
So I think this question is perfectly explaining to us that anytime light is traveling through a different medium, apart from a vacuum or air, it's very slow. Is that okay? So we pass this light through a chloroform and it's traveling about 1.99 comparatively to 3. That is very, very slow. Is that okay? So this is a very nice and a practical example. About how to leave your answer, I think 3 decimal places is fine, unless it's an objective that we have options to take from. Is that okay? Now let's look at something here. We'll be looking at something called the Fermat principle. I've done a whole lot of essay writing here for your understanding, but I'll do a very brief explanation of this. Very, very brief one. Supposing you have a pool here, and you see every pool too, they have a ladder that helps us to descend down there. Yeah. And let's say you are here. No, you are here. And of course you can swim. And you hear of an emergency of a child drowning here. When you are going, are you just going to dive yourself in here to rescue the child, or you are going to pass through this end for safety measure purpose? Descend, then go and rescue the child. Which of the options are we taking? Now, only swimming there.
I the emergency, but I want to be time I'll be do stay on the night that I dead body. You have to die for the sake of the emergency. For me, that's the common sense that I would do. I don't know other people.
I think if you go through the same process, I know I can overcome into maybe emergency call for emergency action. So even if you cannot do it, you just need to do it because of an emergency. So you just dive and move through that angle without escaping the process.
So when you dive from where you would dive to where the child is, it's shorter than going through that long length to go and descend the staircase. And more time to be needed. By just diving straight, the time is very short. The length too is very short. It's shorter, sorry.
You don't know how to dive and you accidentally hit your head.
To take the shot.
Where the child is, you can't hit your head.
Then to that, you don't know how to swim. And if you don't know how to swim,
They say I'm more the assumptions, baby. But anyways, your submissions are very right, and these are the answers that I'm looking for. We are looking for the least time to travel. Is that okay? Comparatively, you know, when we are talking about reflection, we have a plane mirror here. Light hits on it, and it goes here. But what Fermat was looking at is the fact that can we have a least time of travel? Let's say we are from this point A. We want to reach a point B here. Do we have to go all the way from this end before we can go to this end back? Why don't we travel from this end straight to what we want to go? Then that will be all. So he was trying to use this least time comparative methods to solve for an issue or proof for reflection and refraction at the same time using the least time situation here. Is that okay? So now let's look at the scenarios that he gave and the mathematical procedures he followed before reaching there. Please, can I go on?
Yes, please.
So now we are at point A. We want to go to point B. Fermat is saying we should go straight to this end. But before we do that, let me show you something. We are going to consider these parameters. This is a normal reflection on a plane surface, so don't get confused. The incident ray, the reflected ray, we have the angle of incidence, we have the angle of what? Refraction, a reflection. Is that okay? Now we are considering the height of A to our plane to be h1. We are considering the distance of A to our point of incidence to be x. And the whole distance of travel that Fermat is talking about to be L. Is that okay? Now, if here is our x, here is our L, and we want to find this distance, we just have to subtract the x here from the L, and we get this short distance. So it's going to be L minus x. And of course, we are going to consider our second height of B to be what? H2. Are we okay with the parameters I've mentioned? Now, let's look at something. We are just going to use, before I go there, we are just going to use Pythagoras theory. If Pythagoras told us that anytime we have a right angle triangle like this, and this is our A, this is our B, and we have our C here, what would be the formula? Do we remember?
Yes.
Yes, please. A squared.
The square of the A equals the square of the B plus the square of the C.
Perfect. Now let's relate that one to what we are doing here. We still have a right angle triangle here. Now the distance here is AP. How can we define AP in terms of Pythagoras theory?
Hypotenuse. So AP squared
From
is equals to
square root of
X.
Square root
of x
squared
plus
h squared. H1 squared. H1 squared.
H1 squared.
Perfect. So we have the square of the x and h1 squared. Now, can we also look at the other one as in the BP?
BP
equals
square root of H2 plus
squared.
H2 squared.
H2 squared plus L minus X
Minus
squared
x
Bracket
into
open.
Put it
bracket
in
squared.
bracket.
plus into bracket L minus X
X
squared.
all squared.
All squared.
Bracket close. All
All
squared.
bracket close, all squared.
Perfect. We are done. Now, if we want to define L is the distance between from this end here to this end here. So we can simply add A, P, plus BP. Please, are we okay?
Yes, sir.
So it
Sir,
means
please.
ideally.
I have a problem with that one.
Okay, tell me.
Because I think the hypotenuse is always longer than the other sides. So
Yeah.
why don't we rather use the same Pythagoras theorem to find the distance horizontally, the horizontal distances, so that we can say the L equals the X plus the L minus X, rather than the AP plus the BP.
Here, what you're saying is very right. Here, we are looking at it in the perspective of Fermat. Is that okay? Because Fermat is saying that, and we can't even use Pythagoras because we are not very sure about the distance of this one. Fermat is saying that A is traveling to B, but it has to pass through the normal before it goes here. A is trying to solve this one by just traveling from A here straight to B here. And that is the distance that we have as L. Is that okay? So we are deducing this one at one end here, and we are deducing this one at one end here. And we use Fermat's assumption to prove for what we are looking for. Is that okay? Who are you repeating?
Frank, sir.
Okay. Are you okay, Frank?
Yeah, I'm okay.
And that is what we
So
have.
even if you want to use that procedure, when you put a change of subject, you set L to be 0. So there won't be anything to find.
Okay.
If you want to change the subject, you set the L to be 0. It becomes L minus L. Where I don't where it is 0, so it can't be applied.
So, so maybe if I am using the L to just confuse you, we are just considering the distance travel. So I think I did it D earlier. So let's use the D so that I'm not confused with the L. But at the end, we just wanted the total distance traveled. Is that okay? That is from A to B. And I've explained to you. Please, some of us have some backgrounds. Can we mute? I beg. Now we all understand how we managed to get this. We all understand how we managed to get this. Now we are combining the two using the distance traveled from Fermat. Is that okay? So we are combining what we had here. If we look at this thing very well, hold on. You know that anytime you have velocity is equal to what? D over T. Am I correct? And since we are dealing with speed of light, it's going to be C equals D on T. And because we have our D here already, we are just going to do a small substitution. So I'll go to the next slide. Now, we are interested, what I had before, I had C equals D on T. So just making this one the subject, and substituting it here, we are going to get our t here, because when you make d the subject, we are going to get dt. Is that okay? Then we bring the ct in place of the d. Is that okay? So here d was here before, then we brought ct, and we've made the t only stand alone, and we have c down here. Am I confusing you guys, or you're okay? Okay, perfect. So now we have t to be the whole of this equation now. Is that okay? And remember, we had this one from AP, and we had this one from PB. And the next one is where the confusion may start a little. Now, because we want to minimize the time of travel, which of course we know that is going to be small, we want to find the derivative of this x with respect to distance, that is x. Is that okay? So it means we have to find the dt of this with respect to what? X. And I think this is where our problem will start a little, because I'm sure most of us has forgotten derivatives. Find the derivative of something. But can we find the derivative of what we have at the top here, this first term? Is it possible?
Oh.
Can we do it or assemble? If we have x squared and want to find the derivative of x squared with respect to x, what are we going to do? 2x. If we have 2x cubed and we find the derivative of it, what are we going to do?
6x squared.
6x squared. 6x squared, perfect. If I have x and I want to find the derivative of x, at the top here I have 1 over 2. What am I going to get?
I have x exponent 1.
No, you have 2 exponents, -1.
That going to get
half x over root of x.
This is going to be the answer, or?
Yes. That is it.
Because this one's supposed to come down here.
Yeah.
Then when you finish, we subtract
1 from down.
1 from. Okay, so and we're expecting something like this. It is the same situation that we have here. We can break this situation down so that instead of the square root, we get h squared 1 plus s squared. One over 2. Because square root is 1 over 2. Now, from our small understanding that I've explained right now, can we find the derivative of this?
It's going to be
That will be h squared plus s squared over 2. Exponent negative half.
Negative half.
Okay, let's hold on. I'm giving another question. If I want you to find the derivative of this, What is it going to be? Let me put another square here. Or maybe let me just do... What is this one going to be?
It's going to be
2.
1 plus power 1.
2 plus 2x.
2 plus 2x
2 plus 2x
and
raised to the
power
power
1.
1.
Power 1. All to the power
2 plus 2x.
2x, no power.
2 plus 2x all raised to the power 1.
Okay.
2x bracket. 2x 2 into bracket. 2 into bracket.
1
1
plus
plus
x.
x.
I think if I don't take time, we may keep on this a lot. So I'm going to do a shortcut here. But I
2
beg
into
of you,
bracket.
let's go. I beg of you, let's go and check this things out again. I beg. Now let's look at what we have here. When we find the derivative of the first term, we expect to get x. No, let me just circle it. We expect to get this whole term. Is that okay? When you find the derivative of the second term, we expect to get this whole term. This is in your slides. Just take your time and go through derivative briefly, then come back to this one and confirm the answer. Is that okay? I'll be here if you have any problem, but I don't want us to waste time on this one. I beg of you. Please, do you agree what I'm trying to tell you?
Oh, yes, sir.
This is quite simple. The only thing that we have to do is to find the derivative of what is inside here and bring this one down here. Then when you finish, you come and subtract this one by 1. But I wanted you to understand these principles before telling you. But I think we've lost track. So.
Hello, sir.
Yes, sir.
I have 2 questions. The first one is how you have the whole, term here divided by C.
Okay.
So I'll beg you just go back a little and give me that one.
Can someone help me here?
I got lost. It's just right there. C is equal to D on T. Yeah.
Okay. So let's look at what we have here. You see, this is D. It was D before.
Yes.
And I told you that if you have velocity is equal to D over T.
Sure.
But because we are dealing with speed of light, we don't need velocity. We can just bring C straight away. Now from this term, I can make D the subject. Then I'll get D to be equal to
CT.
Now I'm ignoring the D. I'm bringing this one here. So now cancel the D. Then let's bring CT. Now if I make only T the subject.
Okay.
If you make only T the subject, the C will become the denominator here. Then it will come down here.
All right. I got
and
you.
That is how we manage to get this one.
And the second question.
Come.
How did you know that at this point you do differentiation or find derivatives?
I say, how did you know it? Okay. The way you even ask the question, I don't know how to answer this. If we have, in fact, I made a condition here.
Okay.
In terms of light traveling, we expect a very small time. And differentiation and say the limit of something is to help us in measuring like something like instantaneous, something very small. Is that okay? That is why we are trying to bring in the derivative here on board with respect to x here. Is that okay? And the x here is representing our the x is representing distance here. Is that okay? That is why we have here. We are doing the derivative of it with respect to x before we can continue.
Okay.
So please, let's go back. Then let's go through our differentiation. Like, just don't go and read everything, but just know the basic rules in finding the differentiation. And we will come back. You come back here, then you come and try and see if what you've done it's the same answer that we have here. Is that okay? I beg of you, let's do that. But let me do this one briefly. Only this one. If you have a situation like this and you want to find the derivative of it, the first thing that we have to do is to find the derivative of what is inside the bracket. And here is with respect to x. So h, derivative of h becomes 0. Derivative of s squared becomes what?
2x.
2x, thank you. Now that is the first thing that you do. When you finish, you have to find the derivative. Bring what is the top here down. That is the 1/2. And you bring your whole set again. That is h1 squared. What is in the brackets? Bring everything again. Plus s squared. You close the bracket. Minus 1/2. Because we are subtracting 1 from the half here. And this is what we're going to get. So the 2 here is going to cancel this 2 here. But we have x here. So the x here will stand. But now we have negative 1/2. So the negative can make this whole term here a denominator.
Yeah.
Please, are we okay?
Yes.
And it's making it a denominator. That is why we have it down here. And the 1/2 makes it a square root. Is that okay? In fact, when you go through the same procedure as I've explained, you're supposed to get to this term again. Are we a little bit okay?
Yes.
Sir, please, would they tell us to prove the formula, or we are
To
just
prove,
going to
yeah, that's my question.
Yes, you can be asked to prove. It's in your model and your syllabus, so I have to teach you. Now we into now all boa. Yeah, 7 grade.
This
one,
a baby. A baby, you see, a baby. A baby.
Please, I'm left with only 15 minutes. Let me try and see if I can finish up here. I think we still have a lot to do. Even another one.
Sir, you say take your time and then we draw near upon, then we go. Next week we continue.
Hello, sir.
So
yes.
Hello, sir.
Yes, madam. What is?
Please, can you share the slides again? Because I don't have it. Or if anybody is having it, can the person share it with me? Or on the switch platform.
Please, if anyone,
we share it on the listing for you. We'll put it back on the platform.
Thank you, sir.
Okay.
We'll put it on the platform for you, okay?
All right. Thank you.
All right.
Please, can I go on?
Yes, please.
Perfect. So now at least I've solved this one for you. It is your task to go and find this. Is that okay?
Sure.
In fact, When we finish, we are now approximating this one up to 0. After getting this one, we can just send this whole term here to the other side of the equal sign. And this is how it's going to be. And because we have C here, we can just cancel the two C's. Exactly. So that to be left, it's only this term that we have here. Now let's look at something here. If I have a right
screen
angle
is not showing.
Come again. Is someone saying something?
No, please. No, please.
If we have a right angle triangle, we want to use a little trick here. We have Y, we have X, and we have Z here. And supposing we have our angle here. Or better still, I don't want the angle here. Sorry, I'm putting the angle here rather, at the top here, theta. If I want to find the sine theta, but this time around, I'm interested in bringing, let me see, Y and X on board. I want a trig formula that brings X sine and the theta. Let's forget about the Z.
You use cos theta. Cos theta equals
X over Y.
X over Y.
Okay. Cos is what?
X over Y.
X over Y.
Well, in cos
is car. Adjacent to
Adjacent to hypotenuse.
Okay.
Sine. So,
Cos theta.
X on
X on Y. What if you want to use sine?
Sine is so
will be opposite of hypotenuse.
That one be
Opposite
Z.
of
Because we are not interested in Z.
So now let's hold on to that. I'm going to bring another angle here, and the angle here, I'm going to call it phi. Is that okay? So now with the phi, I'm interested in X and Y again. What would be sine phi?
Sine phi will be X over Y.
X over Y.
Yes.
Perfect. It is the same thing that is going to go on here. When you use the sign, that is better. In fact, what we have here, we can close our line like this and create a straight line like this. And the H1 that we have here can be the same H1 that we have here. And the X that we have here can be the same X that we have here. Is that okay? In a situation like this where we have our angle here, what is going to be our theta 1?
It's going to be tan theta 1 equals X over H1.
No, I want us to consider I want us to consider AP and X.
Okay, then it's going to be sine theta 1 equals X over AP.
Very good. So it's going to be sine theta 1 equals what?
X.
Opposite on hypotenuse.
In this case, why? In this case,
X on AP.
X on AP. But do you remember what we had as AP? When we are using the Pythagoras theory.
Square root of
Yes.
H1 squared plus S squared.
Very good. And when we put that one down here, do you know it's going to be the same as what we have here? Do we agree to that?
Oh, okay. Then let's use that one.
So it means that in place of x over square root of a squared plus s squared, I can just write what? Sine theta 1.
Okay.
Yeah. Now let's go to the other side of the equation. Supposing we draw this one, go end here. Then we have our b here. We have down here to be L minus x. Then we have our h squared here as usual. In terms of sine again, that is sine theta 2. What is going to be the answer?
Sine theta 2 was L minus x over BB.
Very good. And we already know that BP is square root of h squared minus plus into bracket L minus x all squared. Which is the whole term that we have here. Agreed?
Yes, sir.
So it means we can write sine theta 2 here. In fact, we are almost there. But we have to do a small assumption here. And the assumption here is considering a very, very small angles. If the angles become very, very small, it means that any angle that we put in sine theta here is going to be the same as the angle we get here. So if that is the case, our signs may go off into the theta that we are considering. That is getting theta 1 to be equal to theta 2. And which law does this one reflect? The laws we've done under optics now.
Law of reflection.
Law of reflection.
So this is a pure demonstration of Fermat using distances and the least time to prove for what? The law of reflection.
Fermat had one.
In fact, Fermat didn't end there. He did for the law of refraction too. Which it is very, very interesting. But I didn't go through in the slides. I have done a try here. Internet. This week, the more Jumaya. So try your hands for me. Is that okay? I beg. So I think personally I'm tired. So it's left with only 5 minutes to end the class. So if we can end, then I don't know, by next week we will continue, or I'll find time within the week for us to meet again before next week comes.
All right. Right. You're all tired. I think.
Yeah.
But sir, please, do you have some of the past questions with you? If you can share some of them with us.
Yeah, I don't have past question. The only past question I have is the slides. What is in the slides?
Please.
Oh no, I don't have. I don't follow the. I told you I don't follow. I'm not in charge of certain questions, so I don't follow the questions up. My own is I will come and teach it, and I'll just go marry.
Oh.
So, but still ask your senior colleagues. They should have past questions. Is that okay? I beg of you.
Benjamin, I hope you have past questions.
No, please, I don't.
Okay, so kindly permit me to log out. I will see you hopefully in the subsequent days. Have a nice evening.
Thank you, sir.
So one here,
my hands is already up.
Chemistry de menam ha physics de menam ha na wuawi o.
When you here, I'm up for physics no would any man on aja no we ain't here.
Say my brother me hu na bia me fa.
Please,
Physics and chemistry.
I'm continuing from where sir.
Master, me koye Ghanaian
And
language.
then I'm continuing
I
from
know
where
that's a oh yeah, that's a big boom.
30 minutes, 30 minutes.
Me koye Ghanaian language. Why?
The lesson is being recorded, so if you could pause.
Mr. Paul and Mr. Samuel Dugu, Mr. Mumwan, once I'm interview.
They say on one.
Oh, mate, for be brew away. Oh, mate, for be brew away. We see for the
Group work be group we been using a kakran cry.
Those from
no way
please, can you help us
online say
with
ya.
I say yeah no online me watakwa meet me ba baby am.
That proving because they be hard you.
You be a bachelor, maybe I will be another.
Priscilla will lead the discussion. No, Priscilla, lead the discussion of mine.
Oh my God.
Yes, I'm be more approve you what.
Let's assume. Lead you know lead discussion no matter Priscilla.
Hey, I don't know.
Me sure in my lesson
From Alpha to Omega, A to Z.
Yes, I have such a mission. I know as a mission.
Cause him in do baby, I'm here, Papa.
Oh, man, Papa.
Sir Frank,
this is good.
What the subject that the Sir Frank, I didn't you.
Into when you see the application way.
I want him fine.
What about photographer?
Photographer no way we GSS no. Oh my goodness.
Let's assume.
Event planner.
Please, when the mental and contact seniors now more questions in mind.
Yes.
Madam Priscilla.
I've heard that you can change your course.
Madam Priscilla, they were talking about
maybe I was
oh, see, what's the top course Sunday, baby?
It's too late.
Mrs. Amekoye history.
Oh,
history.
And yes, I'm so I'm interested. Chief for the family.
Let's assume. I don't matter more for Nasi.
This time, you know, you're teenagers, it's a mapos where was an easy.
I drink crime, my own to me transcends here. There are some more.
Also, be at the course for answer. Wawario, and yes, easy.
Already, no, I'll be breaking cabo move. I didn't know.
School fees is true. Well, what dear? Collect school fees. Mama, ya fa slice people they just to corner too. If you don't get the discussion, say some machine poor. Yeah, sacrifice it.
And your pet slice no
This will
this will be Lidio. Like will be Lidio no agenda numbers when I gather one
me
side.
push out to some amount.
I just a man
print you.
I just a man sorry and
Slides, they are two.
Which one is the big one?
They use this one. There's a lot of questions inside as compared to the lectures. So.
Okay.
There are two.
No, I'm talking about the one he was using to teach us.
That one is the normal one, no.
Hey, which one is the abnormal one? Let's know.
There's another one. They have been written down said colleges of education UCC math and science.
I know you're near colleges for you so.
I know what's go.
That's for code.
Hey, and the telescope to super and yes,
we can all come together. So maybe some 2 hours before you all go to school.
So which one are you using?
Or maybe
are you using that one or we are using the lecture only?
So we will combine them.
Combine them.
Be told that what the lecturer is using is simplified. That one you can go and take it, and there are certain things you may find difficult to understand. One of the questions you can go for the code one. You get ample questions in there, but for simple understanding, I think his one is better. Because how code will be ready a book is some way view.
Boost no crowd here. What kind of count here say mistakes be brain?
Code for code your books is something. I mean, I prefer the slide in a slide, and you listen to
the audio.
For questions, we can pick up from those books, but for you to learn that book, to condition your prayer book,
but your group and model too soon.
Slide now.
I'm trying. Slide.
Now, please.
You
want to have a group studies, please.
That's what I'm still campaigning for.
Please,
if
you can put the groups so that we join.
No,
it's only
group the answer now.
Group me major of physics.
Into phantom physics major also.
Physics major. No, what center.
Wow. I'm here now quite different area. UCC center now. When you say the same idea.
For number one mention or high on, then we pick it from there.
Okay, 0242.
0242.
86. 4475.
475. 0242 86 4475.
Very good.
Thank you.
Send me
what's up, I'm Gideona.
Okay. Okay,
So,
Gideona me
let's all conclude on the group studies now.
One person should create a platform. If those of us agree to do it, let's say that person have the numbers from here. Non-creative platform, no. It shouldn't be on the normal,
Those should be
numbers.
What's it?
The better than your own numbers.
We'll be living number of mention anymore.
Okay.
Olivier.
Comment
session.
Comment session.
Oh, okay. Okay.
What's your name?
Please, so is there anyone from
I'm not sure.
Ghana Center?
No, I don't want more of Takrady people, or even Takwa people, so that you can meet at my
Here's
school.
the case. We all started. It's something else.
And so the only thing that will help us is the
Yeah, no, they see
online.
the comment section. Remember one number Mr. Moa.
Hey, issue. But maybe I will anyone.
055
Maybe
55
1474
1474
1474
1474
895 5.
Please, can you see
Benjamin.
mine?
Yeah, Priscilla, yours is there.
We cannot see you, so Madam Priscilla. Benjamin, we did the Benjamin.
Benjamin, no. Benjamin, well, comment section, what you cannot see somebody's phone.
055 055 1474
Okay.
895.
Okay.
But
when a bit petty platform now.
Former Priscilla.
Jerome can see it. Jerome no, also yeah, no number. Jerome Jerome me kind.
Short of the number no.
What do you want?
You mentioned my name like that.
Violence.
It's because of your voice. Don't mind them.
Hey, now that.
Oh, but seriously, Priscilla, you have a unique voice. That's like the Bian personal house out.
Oh, dear mo. Priscilla, don't mind them.
How many people so far? I think is it 5 or 4?
Let me check.
5.
But we are more than 5.
1, 2, 3, 4, 5. Okay, Benjamin's phone is there 6, and then Annika, sorry. So 7. It's 7.
Really?
Yeah, Benjamin's own came twice. I typed his own, and then Jerome too. Jerome, sorry, also. Or Jerome.
Please, Jerome. It's not Jerome.
It's what, Jerome?
Yeah.
Jerome.
Yeah, Jerome also typed it. So we are 7 in number. It's a bottle.
So to
I thought you were sleeping. Okay.
So we'll meet over there, guys.
Sure, we have to, and then decide on the time.
Sir Frank will be our physics master, Sir Frank.
Okay.
Yeah. Sir Frank by Madam Priscilla.
Assisted by Madam Priscilla. Madam Priscilla will be assisting you.
Yeah.
With explanation.
So I course rep for the internal physics students. So before that.
What Madam?
It's hot water. Sorry.
Course rep for the internal physics student to be Madam Gideona.
Okay.
I've already mentioned Priscilla's name. I don't want her to be.
No.
Why did you change your voice like that?
Priscilla will be assisting Frank, so you have to take the mantle.
Okay.
Will be assisting Frank.
I'll be assisting Frank at where? I didn't get what you were saying, no.
Okay.
The course rep. You'll be the course rep for us. So any information, if there is the time for us to meet, you put it on a platform for us, then you know.
Is it group studies or?
Yes, madam.
Yeah.
Group studies not only on physics, but I think all other subjects will also help.
Me, I'm at West Coast Center.
Oh no, no, we'll do it online.
I know
We'll do
you,
it online.
You and your sister.
Hey, family planning. Family planning.
Yeah, I met her. I know her. That's why I'm disturbing her. The first time.
Don't be worried about my voice, okay?
Oh, it's like an icebreaker. It doesn't allow us to sleep.
That is how my voice is. So.
Okay.
You have a unique voice.
We are just making fun of you. Oh, you spoil it. Joe. Abanuka, all of you vanish.
Hey. Look at Joe.
All of you go to the go and watch cartoons. Go.
And why are you stacking them?
Oh, they are disturbing me. I'm already tired.
You are tired, eh?
Charlie, since morning.
Since morning, no.
Even the morning session, I was cooking and joining at the same time. In the afternoon, I have to feed them and join. I'm tired. Thank God tomorrow is holiday, so meet them.
Oh. It's good.
You are really doing well, oh. It's not easy, oh.
That's why I said those who have not married, finish with the course. Then after that, you invite us to the wedding. If not,
you will marry now. Oh,
you marry, oh come. I did check the timetable. Even on the 27th and 28th. Oh, it's good. Priscilla, you are saying it's good though. It's very good. But if I knew, I would have finished with all my schooling and everything.
No.
Maybe.
At that time, the would have caught up with you.
Oh no, I'm so young. I mean, do baby.
Look at the way you're enjoying with your husband. Are you not the one cheated on your husband?
Oh, exactly. It's me. Oh.
Love is sweet now.
But brother, now when you want to learn, you have to go and prepare food for the pickings. Then I've done that. Maybe you want to wake up. Then you have to attend to other matters. So
other matters.
Other matters is very important too.
It is, but sometimes when you're exhausted and you know that the physics and especially the hydrocarbons and what have you, is when you sleep and it will be giving you nightmares. You can't even concentrate and do it.
You can go
so it means you've not been enjoying it. Anytime you are being caught up with that dreams, eh?
Oh, bro. Even yesterday, for example.
Hey, Abubakar. Hey, you this man.
You can go on sabbatical leave.
You, I not go talk anything. You, Abubakar, I not go talk anything. You.
And I'm Gideona.
Say.
You say?
You can go on sabbatical.
You should go on what?
Yeah.
Sabbatical leave. For now.
Oh, I will. Now why you careful na Pascal? Oh, fefe na usua de. What about it? That's really because I think one of our lecturer was saying that you can't do this course alone without group studies.
It's very true, pa.
And almost my colleagues who started last, who are going to complete this month, they were all telling me that it's group studies that is helping. Because if you try to study alone in your room, Charlie, you won't get it.
Please, those with past questions, kindly DM it in the group so that we all go through, please.
Yeah, go through.
Well, you know the one saying that you saw some questions via a certain PDF. And then what?
I have few of them. I'll be dropping some, especially with the chemistry. I have few of them. I'll be dropping them on platform.
Senior lecturer.
Yeah. No. Of course, now your certificates and your medals are ready. Go for them.
Now we want physics past questions. Now I think for the physics past question, the West Coast lecture has posted some in our platform. I don't know if you have seen that.
Really?
Yes.
Yeah. It's true. I've joined the West Coast platform. It's true. I saw them yesterday.
Yeah. So
I even tried reading through this dawn.
So through our group studies, I think we can glance through.
Sure.
So Abubakar, where are you located? Which center?
Hey, you people, you come here again. One, where's the rope?
Abubakar.
Yes,
So come on,
Johnny.
put it. If you come, I'll put it in your nose.
Where is your center? Where are you located? I mean, West School or UCC?
I'm a UCC.
UCC, okay.
Please, you're direct to the source, so yeah.
Why? Why do you decide to antagonize me like that?
Don't worry, it's part of the game. There's your whole literature terms, you know that all the bio science. Eh? But it's all literature class and can see who.
I'll follow you guys.
Small. Tell you guys, don't worry.
Oh, it's as well. It's as well.
You be who person any so. You be who person any so. Yeah, the big. Then you so best of it past questions and more like around that. No one survey. You try to massage it.
Okay.
No money be brave. Like a cranny per bidding to you. Eh?
Oh, boy.
I can be.
Charlie. So you guys.
I have a sister. No, yeah, masters was said. She was offering masters at
like most of you are not
is that
on
one of
UCC platform.
You can do it. Physics, group studies. Okay, group studies so that you all know. Please, yesterday the registration portal wasn't open.
I like to open it though.
They did it too. Well, I was checking throughout this. What's the door? They did.
No, they were no my idiot. We can close the door. We know.
Madam Gideona.
Say.
Unless you join the group by invite, so you try and do that thing.
Oh really? Okay. I've not registered for that too. It doesn't. The invitation doesn't come.
Unless.
Okay, I have.
Tell me number one you need here. We came on.
And what is the number?
My telephone number no 055 1474 895. Mo fa min ka group no madaroma.
Okay, so see you guys. We'll meet there.
Okay.
Well, let me try to put the past questions that was on the Westco platform.
Okay. That it's that would be much. Benji. So Benjamin.
Yo, bro. Yes, sir.
Allow you to unless you join by invite. So
exactly. My who message in this here. Let me just attend to it.
Okay.
Please, have you add me?
Allah.
Platform there.
It's physics major study group, I'm sure.
Physics major study group.
Yes, please.
And medical
it's a special platform.
Sorry.
Medical send me message. Giddy.
I've also posted this thing on board.
The what?
The past questions for physics.
Okay. I will meet Castro this evening, 5:30.
Which platform is that?
Sorry.
This one I really
using for
the study group.
Which platform?
Physics
we all have to
Physics and chemistry, right?
Yeah. So we all have to decide when we are going to meet. One person can just decide.
No, we all decide and look at the time that will be appropriate for each of us.
Somebody's called Gideona, right?
Yes, please, me.
Oh, I know my name is Gideona. Sorry. As I'm no quite chatting something.
Oh, Patron said, my promise with Dr. Ben Carson.
Well, Dina no abon. Me a doctor. Okay. Masa enchebia why?
I think.
Incoming.
What I say incoming no enchebia no my invite me some me graduation. My doctorate graduation mumla.
The equation y is equal to a cos.
Physics.
So me the physics now me say ramu. And no
Physics
no
nice.
masters.
Physics nice in you. It's very nice though.
But you see, they are smart because all the courses we also who done if chemistry nko be o for chemistry now.
All the science aspects in your chemistry or into going.
And now
Physicians are talking. My physicians.
I don't like reading. Biology. PTSHS I mean biology. Because
chemistry na me sure. But at least college meet me here no fine. But 10 years.
Wow. And I'm mobile assist here.
For me, I mean biology because I don't like reading.
And I said, my no so no baby, I'll be for be chemistry. Yeah, hi. I'm saying chemistry be a pivotal.
So what we say and go for chemistry no.
Hey, that is
I'm on chemistry.
Chemistry film I say be a physics and let's say biology
but another physics doesn't tell you. Physics and biology so I did be
and maybe a physics and any or maybe only physics and chemistry one student. Maybe a principal
this a principal and then never call.
They never call by force.
Yeah, do call chemistry. Major chemistry.
Chemistry by force.
Yeah.
Cause
media this some
mathematics. Sure. One year
math there. Math because degree no math online. Degree no math teacher no or solve questions na book ni. What the different question on to me
math very interesting. Math very interesting though.
Are you sure?
Yes.
I have friends who are interesting. I even have one in the math department. One lecturer got somebody at college or come one way at the end of a math. The same almost the same on the wall to one or the abajo. Obey this slide in your mouth.
Oh. Me, I went to a school. The math was very interesting.
We are face to face there, yeah. But Nipa no online, no. True, no question about copy. Almost say, oh, you're lazy. Some of my friends do math. And I mean, that's I know one of them. Doctor me.
But you can't change it.
Yeah.
I know you can't change it.
They say you can't change it.
You can't.
You can still change it.
You can't do that. You can't do.
Once you are registered, you cannot change you.
Maybe home econ students are doing chemistry, so no biology, chemistry compulsory.
But this is some of the SHS from biology or chemistry. You're optional. You choose one.
The clothing people do chemistry and the food people will do biology.
Yes. Now, if they tell you the number of the amount of things they are buying, the cost, so because of the particles, apron in cooking utensils.
Wait till you buy some. You buy lab coat.
Is it the switch?
Yes, you buy
our colleague switch people are doing the chemistry.
My lab coat, the same to my go and one no.
Hey, me I say chess there. Kwame Kofifi himself. O say.
Listen. Young colleagues now, switch in home econs. I don't know biology and chemistry, nana.
Yeah.
No, one on why biology and chemistry. It's a clothing now, be biology, chemistry. Now one way your food no why biology. Watch out. It's the body is equal when you cry. I bet no chemical equation. I didn't know.
Please,
Red
can
onion.
we change the course? Just find
You
out
can't
for
change
me.
it. You can't change it. For now, you can't change it.
Priscilla, you are in
It's
the
too late.
middle of the sea. Oh. You are in the middle of the sea.
It's either
You continue or you get drowned.
Just
it's
you
either
need to
it's either
continue.
you dive into the sea or you stay calmly on the boat and then they sail you out peacefully.
Uh-huh.
So it's the boy is in your court.
It is well.
The boy
So
is in your court
maybe
now.
I think we'll continue on the platform and then decide when, or
Sure.
we can decide
My
now.
people, I've not been able to locate the platform you are saying. No.
Oh, please,
Oh,
it's
we just created it. Oh, it's not an existing one. We just did it.
Say hi to
Then you
me
have to
and
add
I'll
me,
add
please.
you. Say hi to me, I'll add you.
yes. Course rep is talking. Say hi to me. I will add you.
Please,
you
how
are
will I say hi to you?
Say your number
Please, I
is
don't have your number.
your
Hello?
number.
Yeah, so let me give out mine.
Your number is
Yeah, you remember it's still on
0555.
recording, though. You remember it's
Zero
still on the
5.
recording, though.
It's still recording, eh?
Yes, it's still recording.
They'll take it out. They'll take it out. Don't worry. They'll trim it.
Oh, they'll take it out. They'll take it out.
They'll trim the video. Don't worry.
Mm.
Your number again.
All right, so 0355. Yes. 0355.
Yeah.
012.
01 703. Okay.
Yeah.
Teacher, that's a Professor Abubakar. Professor, right?
No, prof.
Yeah, prof.
Prof will be teaching
Yeah,
us.
I don't like attending class on me.
Do you like attending class?
You don't like what?
Oh, boy.
Oh,
I have
Chad.
certain so be as no online class. Hey. Oh. Ja. They be a member will be Abubakar Sheho. On Madam Priscilla and Madam Gidiana. They be a more.
Bof, won't you see my profile picture? No, won't you?
Do you know what I do? Do you know me? I only show my presence.
Me being in class. Now you have to be punctual. The punctuality will also give you a max. That is why I'm always punctual.
Allah, that's a West BBI. Hey, group way.
I only come there to show my presence. Finish.
It's true. I asked one of my lecturer, the one who is taking us the physics.
Yeah, bro.
You have to be punctual.
Yeah, please, unless you join via invite, so I'm sending you the
and
link.
Unmute yourself and do whatever that you want to do. Just want you to see that you are a part. That's all.
Hey, Madam Gidiana.
Say.
Princess saying what is Madam Princess saying?
I'm just reading what is under your profile picture.
Actually.
Your WhatsApp line.
Leave her alone. No, she's a married woman. Leave
your
her
WhatsApp line.
I beg you. But no one is.
But that's not bad.
Leave her alone.
I'm just trying to compliment her.
He's complimenting my comments on my profile. I said I love my husband, and that's a fact.
Why are you sending your mind to Madam Priscilla? I beg you, please.
It's not me.
Oh, Charlie. So let's meet on the platform, guys, so that we will know what will happen.
Okay, so you
yeah.
Sure.
All right.
Bye.
Bye.
Me? What are you saying?